Okay, Christina Felix will start, he said.
Okay, good to know. Thank you. I will disable the waiting room, so.
Okay, good morning, everybody. I hope everybody can hear me.
Yeah.
Yes. So let me introduce this mini colloquium that's organized within the Condensed Matter Division 2020, which is organized together with the Condensed Matter Division of the Spanish Royal Society of Physics, the GEFES. Okay, we are very happy. Oksana, Paolo, and myself, which were the main organizers. Although I have to excuse Paolo, he just had a baby. So unfortunately, probably he won't be able to make it. But he was one of the, let's say, the main organizer. So, Oksana and myself took over after this incident, let's say. So this mini colloquium is organized in 3 different days, from today to Wednesday. We will have morning sessions from 9:30 to 12:30. We will have 8 invited speakers in total. Okay, 3, 3, and 2. The others will be contributed talks. And then in the afternoon of Monday and Tuesday, so today and tomorrow, we will have a session of pre-recorded talks. This will be from 5 p.m. to 7 p.m. in the afternoon. And what we will do we will play the recorded talks, and then we will have discussions as it was in the poster session. So whoever is interested, we will explain it in more detail in the afternoon session itself. Okay, so now it's time 9:30. This session will be chaired by Professor Kim in Sakai University in Paris. So I hand the chairing to Professor Kim.
Okay, thanks Felix for this introduction. So welcome all to this morning session of spin orbit physics in condensed matter. So we have this morning 3 invited talks and 3 contributed talks. So invited talks, just as a reminder, 30 minutes of talk, 10 minutes of questions. And so I have the pleasure of introducing Professor Matthias Klaue from the University of Mainz, who will begin the session with his invited talk on anti-ferromagnetic insulatronics, spintronics without magnetic fields. So the screen is yours, Matthias.
Okay, well, thanks, Jovan. So you can all see and hear me? Perfect. So firstly, of course, I'd like to thank the organizers in these difficult times for putting together a really, really nice program. You know, everyone expected this a year ago to be different, but I think we'll make the best of it. And I've also learned that it can be quite fruitful that now people can participate that otherwise might have found it difficult to go to Madrid, even though I still hope that one day we'll all be able to meet in person again. Yes, so indeed, today I'm going to give, as a first speaker, a brief introduction, or not so brief, like half an hour, 35-minute introduction into what's new in anti-ferromagnets with some focus on spin orbit effects. So I've termed the presentation Writing, Reading, and Transporting Spin in Anti-Ferromagnets. And I'm going to particularly try and show you how we can functionalize anti-ferromagnets and make them useful active components. And this includes, in particular, how to read information in antiferromagnets, how to write information, and how to transport information. And in particular for the writing, already as a spoiler, a lot of this will actually be covered by the next talk by Helen Gomonai, who's been quite instrumental in some of our joint work. And therefore I can actually just give you a very brief introduction, and all the nitty-gritty details, including the deep theory, will be covered in the next talk. So just a one very quick slide. So I'm a IEEE Magnetic Society Distinguished Lecturer this year, and as part of this, I try to promote anti-ferromagnetic spintronics. And I just give you one shameless advertisement for the IEEE to show that this is a large society, learned society for magnetism that does many things, such as publishing journals, making videos, organizing summer schools, and so on. And there are also 2 online seminar series, which I think are very nice to keep in touch with the community. So if you're interested, go to these links and join the online series. So let's start with the talk. So why are we doing anti-ferromagnets? Well, you might all know this person. So this is Louis Néel, and Louis Néel said in his Nobel lecture in 1970 that anti-ferromagnets are interesting but useless. And I think we all agree that they're interesting, and I try to convince you today that maybe they're not as useless eventually as magnets. So firstly, antiferromagnets have certain advantages in terms of stacking density. So that's something that you might all be aware of. If you have a ferromagnet, then in a ferromagnet, there is an interaction due to dipolar stray fields. So this bit here at the center has a different environment than this bit here at the center, because the two neighbors here are pointing in the same direction, and here they're pointing in the opposite direction. And that inherently reduces the stability due to bit interference. And in antiferromagnets, this is very different. You have compensated sublattices, so there's no net stray field. However, also in most antiferromagnets, there's no difference between right and left because the two sublattices cannot be distinguished. So to store information in an antiferromagnet, you have to rotate these two sublattices by 90 degrees rather than the 180 degrees in a ferromagnet. So that's a fundamental difference. Okay. Now we all know, because it's a magnetism session, that an antiferromagnet, the susceptibility is much smaller, but it's not infinitely small. So it's like 3-5 orders of magnitude smaller than you have typically for a ferromagnet. And that just means that the antiferromagnetic sublattices are not very affected by applied magnetic fields. And why is that? That is because if you look at the energy scales, the highest energy scale is actually the antiferromagnetic alignment of the two sublattices that you see here, which is of the order of 1,000 Tesla, and that sets roughly the transfer susceptibility. And then you can also have a strong exchange within a sublattice of, let's say, 100 Tesla. And these two numbers don't need to be so different. That sets the Néel temperature. And finally, the only temperature scale, the only field scale where we can actually do something in the lab easily is the anisotropy that sets this so-called reorientation of the sublattices. So that is something where we can actually work in the lab, whereas these two are so strong that usually we cannot access these in the lab. Now, this very strong coupling between the two sublattices also leads to the fact that the eigenmode frequencies are a couple of orders of magnitude faster in antiferromagnets than in ferromagnets, leading to this very exciting dynamics in the terahertz range. And something that people might not be so aware of is that ferromagnets are not that abundant. I mean, we have iron, nickel, cobalt, maybe we get lithium at low temperatures, and then some compounds and alloys, but there are many more antiferromagnets. And that's because there are many insulating antiferromagnets, whereas the ferromagnets are usually mostly metallic. There are very few exceptions where they're really insulating ferro and not ferrimagnets. And why is it that we have so many more antiferromagnets? Well, that's because there are many, many options on how to generate an antiferromagnet. So you can see here that if you have an antiferromagnet, you just need a zero net magnetization. And that means, for instance, you can have a layered antiferromagnet, whereas in one layer, all the spins point up, and in one layer, all the spins point down. And then you can have a different version where you have within a layer up and down spins. However, in all the layers they're the same, or you can combine both, where you have within a layer different orientations of the sublattices, and then also in different layers these switch as well. So these are very different orientations, and these are actually realized in reality. For instance, in nickel oxide, we have a typical layered antiferromagnet, whereas in one of these 111 planes, the spins are all pointing in this direction, and in the neighboring 111 plane, the spins are pointing in the opposite direction. And now what is important, that in nickel oxide, we cannot distinguish between these two layers. However, there are also systems such as manganese to gold, which I will go into in a bit more detail later, where you can actually distinguish between the blue and the red spins, because the two atomic positions are not identical, not equivalent. And now these are all systems where we actually have so-called collinear antiferromagnets, meaning that all the spins of the two sublattices are pointing either in the parallel or anti-parallel direction, but you can make life even more complex by going to very exciting non-collinear antiferromagnets, as shown here, where you see the spins point in all kinds of directions, but again, within one plaquette, the spins actually cancel out to zero net moment. And then for the ultimate complexity, you can have non-collinear and non-coplanar antiferromagnets, where you see here that there are spins which pointing out of the plane towards us or away from us, and that just makes it extremely complex to look at these type of systems. And today I'm just going to focus on these collinear antiferromagnets and not on the non-collinear antiferromagnets, because for an introduction, these are already complex enough for myself. One other thing that I learned actually from Helen Gomonai is that the mini-to-elastic coupling in most of these antiferromagnets can be relatively sizable, whereas in ferromagnets it's comparably weak. And finally, as I just showed you, the coupling that leads to ferromagnetism is usually simple Heisenberg, because you want to have all the spins parallel, whereas in antiferromagnets, it can be very complex. In this non-collinear, coplanar antiferromagnet, you have a lot of different exchange integrals, which yield very complex overall coupling. So useful, yeah, obviously we all know that ferromagnets are useful. They're used in memory, in sensing, and so on. Whereas antiferromagnets, so far, they're primarily useful as passive elements. They're used for exchange biasing, hard layers, and spin valves. But they are not easy to use as active elements because they're hard to measure and hard to control. And today I want to show you that antiferromagnets are definitely interesting and possibly useful even as active elements. Okay, so this was a brief introduction to antiferromagnets. So now let me show you one slide. If you don't take anything home from my talk today, then please remember this one slide. So ferromagnets are being manipulated, for instance, by magnetic fields, which is 19th century physics, whereas antiferromagnets can be actually manipulated by complex spin orbit effects, which is 21st century physics. So just, take home, this is very exciting, this old school. Okay, so let's start with the physics. So first, in order to make such an antiferromagnet useful, we need to be able to read out the information. So how can we do that? One way is so-called X-ray magnetic linear dichroism. X-ray magnetic linear dichroism means that if you have circularly polarized X-rays for a certain energy, then the absorption of these X-rays depends on the alignment of the polarization of this linearly polarized X-rays and the direction of the two sublattices, so-called Néel vector. So if we have these two sublattices, then the difference between these two sublattices is the Néel vector. And this allows you to actually image magnetic domains. You see here at 300 Kelvin, we see domains, and note that the bright-dark contrast is now not right-left or up-down, but it's 90-degree different. Black means sublattices on Néel vector pointing up-down, and gray means sublattices on Néel vector pointing right-left. We can heat the sample, then the contrast goes down, and at the Néel temperature, the contrast completely vanishes. So this is some topographic contrast remaining, but that allows us to determine the Néel temperature of this system. Now, of course, it's very nice, but in order to do this type of imaging, you need to actually go to the synchrotron. So if you want to make it useful for a device and you talk to your industrial colleagues, they are not very interested to put a synchrotron in every memory device. So we need some electrical readout. And that can be provided by what is called spin-Hall magnetoresistance, which was first developed in this paper for ferromagnets. And then here's some very nice theory for antiferromagnets. And essentially, if you put on top of an antiferromagnet a layer of a heavy metal like platinum, where due to the spin-Hall effect, you generate a spin accumulation at the interface, then this spin accumulation interacts with the Néel vector depending on the direction of the Néel vector with respect to the spin accumulation. And so what you can measure is the resistance of the platinum, and this will be different whether the Néel vector has a component perpendicular to the spin accumulation or whether the Néel vector is fully parallel to the spin accumulation. And so this should fundamentally allow us to detect the orientation of the Néel vector. And this was actually then done. What you expect to measure is the square of the dot product between the Néel vector and the spin accumulation. And we did this in nickel oxide, where we orient the sublattices in different directions and then measure the resistance of a platinum layer that is on top. So this was first done in the group of Bart van Weesp in this paper here, and then later by us as well as the group of Sebastian Gönnenwein. And we saw that indeed, if you apply a strong field like 11 Tesla to reorient these sublattices, we can get this sine squared dependence that we expect. And if you have a lower field, then essentially you cannot rotate the sublattices due to some anisotropy and pinning. And then you can actually apply a stronger and stronger field and see how much of the sublattices reorients. And we see that about 17 Tesla is enough to rotate our sublattices fully. Okay, so this allows us to now electrically read out even insulating antiferromagnets. Now, how about for conducting antiferromagnets? So if you have a conducting antiferromagnet, firstly, you can then do imaging. That's XMLD PEM of manganese to gold, which as grown has similar amounts of white and black domains, meaning the Néel vector being right, left, or up, down. And if you then actually, and as I'll explain that when I come to the writing part, if you then make all the Néel vectors say point up, down, then you get this configuration where there's still some domain walls or domains where there is some Néel vector pointing right, left, but mostly it's gray showing, or light gray showing that the Néel vector is up, down. So again, we can do imaging, but that is not practical for applications. So if you have a metallic antiferromagnet, let's see if we can also do AMR. And if we do that, it turns out that indeed we can actually get AMR. And the AMR in this case is about 0.15%. AMR meaning whether the current is flowing parallel to the Néel vector or perpendicular to the Néel vector gives us a difference resistance level. So this 0.15 is not a huge AMR effect, but it's sizable, similar to what one can get in ferromagnets. Okay, okay, let me just skip this. So one very exciting materials class that we've been working on are these 2D materials, where you can also do electrical readout. And these 2D materials are exciting because, for instance, in this system here, we actually have, so it's a trihalide chromium trichloride. It's a layered antiferromagnet, meaning that one layer has the magnetization pointing to the right. So if you have a monolayer of this material, it's just a ferromagnet. But if you have a bilayer, then it's a fully compensated antiferromagnet because the two layers are anti-parallel. And if you put a third layer on top, again, you have one layer to the right, and so on. So this is really nice because by doing building blocks of this, you can tune between ferromagnet and antiferromagnet. And we've been looking at a little more complex antiferromagnet, chromium thiophosphate, which is a bit more stable than this chloride. And we can actually also get electrical readout of this. So to sum this up, we can read out antiferromagnets, and we can do this electrically by spin-Hall magnetic resistance for insulators. And in metals, we can do this by anisotropic magnetic resistance and also some domain wall magnetic resistance, which I didn't go into right now. For imaging, we can actually image these systems using X-ray magnetic linear dichroism together with some X-ray based microscopy, such as photoemission electron microscopy. And then there are lots of other techniques that I didn't go into today, such as thermal Seebeck imaging. There's some nice work from Cornell, anomalous Nernst effect, imaging uncompensated moments, second harmonic generation, also Magneto optical Kerr effect, where also we did some work, and exchange bias. And there are also other ways. So actually right now there are a number of quite useful antiferromagnetic readout technologies. Okay, so now let's come to the writing. Now, for the writing, we start with the simplest thing, which is fields. I already told you that actually if you apply a magnetic field, the two sublattices will actually cant very little because this magnetic field is usually much smaller than the exchange interaction between the two sublattices. So here this is highly exaggerated that the two sublattices cant a little bit along the field direction. So usually this is very, very small. However, if we rotate a field, then even though the two sublattices canter very little, it is still advantageous for the two sublattices to be in a direction that is perpendicular to the applied field, so that the little induced moment by the canting is parallel to the applied field. And that's a so-called spin flop field, which I showed you when we discussed the energy scales, is of the order, or can be of the order of a few Tesla. So this is something we can do in the lab. And finally, just for sake of completeness, while we don't look at it here, is so-called spin flip. If you have low exchange but strong uniaxial anisotropy, you can actually get the two sublattices to align ferromagnetically, and that's something, for instance, in the 2D magnets that can happen. Now, I already told you that if you have such a sublattice and you apply now a field, then they will orient in a direction which is perpendicular to the applied field. And if you apply an even stronger field, then they will still stay in a direction that is perpendicular to the applied field and just cant a little bit. And so this is something we wanted to check. For this, we use manganese to gold. Manganese to gold, we can actually apply a strong field of 60 Tesla to orient the spins in a direction up, down, or right, left. So the Néel vector up, down, or right, left. And then we see in the X-ray magnetic linear dichroism spectra that we have first a dip and then a peak. And if we then rotate the orientation by 90 degrees, we get first a peak and then a dip, showing there is this sign reversal, which is exactly the signature of a 90-degree change in the direction of the Néel vector. Again, 60 Tesla is not something you want to put into your memory device. So one option is to apply strain in order to generate anisotropies, because I told you that these anisotropies can be quite large due to the large magnetoelastic coupling. And so here we build a medieval torture device for samples, where we put a sample in here, and then we use the screws to tighten the sample until it confesses or it breaks. And actually it does confess, because as grown, we see a small signal, but when we strain the sample just by 0.1%, we can indeed get an alignment of the Néel vector in the direction of a uniaxis, easy axis that is induced by the strain. However, again, if you talk to people from industry, they're not interested in putting out a medieval torture device into their sample, so they would like an all electrical switching. And electrical switching in ferromagnets is well known. These are spin transfer torque effects, where you inject a spin polarized current, and that spin polarized current actually exerts a torque on the magnetization by transfer of spin angular momentum, and therefore rotates the magnetization. However, in anti-ferromagnets, this might not work, because you see here there is a spin polarized current coming in, and it means one sublattice will actually rotate this way and the next sublattice will rotate that way. So they will rotate in different directions, and due to the strong anti-parallel coupling, there might be no net effect. So what you really want is you want to have a torque that acts on one sublattice different from the other, and this is so-called staggered torque. And this was actually first predicted in this paper here by Jakub Selizny, Jairo Sinova, Thomas Jungwirth, and then first observed in copper manganese arsenide by Pete Wadley. And so fundamentally, this only works if you have a system where the two sublattices are inequivalent. And that is, for instance, the case in manganese to gold, where the blue sublattices and the red sublattices are inequivalent, so that the torque acting on the blue and the red sublattice is different. And the same holds for copper manganese arsenide. So in a very nice picture by Frank Freimuth, you would like to have a torque exerted by a coil which is wound differently along the A side and the B side. So here you have kind of a counterclockwise winding of your coil, and here clockwise winding. And so then what you would like is that these two sublattices then rotate in opposite directions, so that you actually get a 90-degree shift or 90-degree change of the total Néel vector. And this, as I said, was first observed in copper manganese arsenide, and then we looked at manganese to gold, and the prediction is that if you inject a current along two perpendicular directions, then the Néel vector will rotate by 90 degrees in a direction perpendicular to the current. So if I apply current this way, the Néel vector will rotate that way. If I apply a current that way, the Néel vector will rotate that way. And so this we tried out. And it turns out that indeed, if we inject a current along this green direction, which is a 110 direction, or the red direction, which is a 11-bar-0 direction, then we see there is a change in the planar Hall effect, or the AMR. And we see that always the red pulses reduce the signal, the green pulses increase the signal. And when we increase the current density, also the amplitude goes up. So this was published in this paper showing that there are indeed these systems where we can inject currents and actually electrically switch the Néel vector direction. Now, one big problem with these types of systems is that they only work for these crystals which have this inversion symmetry breaking where the two sublattices are inequivalent. So something which would be even nicer is if you were able to switch also an antiferromagnet that has not this asymmetry breaking, because there are not many systems where this exists. So here we have a simple antiferromagnet, nickel oxide, with no asymmetry breaking, and we put platinum on top. And then it was predicted actually in, sorry, let me just go back. It was predicted, let's go back to see the animation again. So it was predicted that indeed by having a spin orbit torque, you can actually move domain walls in this nickel oxide. So this is predicted here and in these two papers. However, the problem is that the direction of the domain wall motion depends on the chirality. And if there's nothing that breaks the chirality, there will be a change in the spin structure. There will be no net switching. And for that, Helen developed a different approach, the ponderomotive force, where you actually have a 90-degree change of the sublattice orientations of the Néel vector, and she's going to talk about this in more detail. Now, experimentally, we looked at this by putting platinum on nickel oxide, and we injected currents along in these triangles, and then we get very complex behavior. Let me firstly say that at low current density, nothing happens. At intermediate current densities, we get this switching as we might expect for 90-degree switching of the Néel vector. And at high current densities, suddenly the sign changes is really weird. So there seems to be a lot of things going on that we don't understand. So here are the three questions. What part of the electrical signal corresponds really to magnetic switching? What is the origin of the non-magnetic signal? And what is the origin of the magnetic signal? And all the details on that you get in the next talk by Helen Goenlein. So to sum this up, we can now write information by doing spin flop if you have a lot of field, by strain if you have a medieval torture device for samples, or by using spin orbit torques, in particular bulk spin orbit torques in these special materials with particular symmetry, or interfacial non-staggered spin orbit torques in insulating systems, and finally also thermoelectric elastic switching, and see the next talk for all the details on that. And now you tell me, well, you know, we have writing and reading, why don't we make a memory device? And you know, we're actually not the first to do this. So Thomas Jungwirth and his crew, they actually made a memory device where here there's a sample in the package, which is wire bonded, and then it's actually interfaced through some Arduino to a USB port, and you can actually write a 1-bit memory. And this might not be very impressive as a density, but it works at 12 Tesla and down to 250 picoseconds. There's not so many memories that work in 12 Tesla. And so the last 5 minutes, I'd just like to show you, to also show you something about spin transport in antiferromagnets. And what we want to do is we would like to transport information over long distances in ideally insulating antiferromagnets. And the reason is that a lot of the power consumption in typical semiconductor devices is due to the current flowing in the vias, in say the copper vias, and that leads to ohmic losses. So if you replace the information by electron motion by the information transport, for instance, by Magnons, so spin waves, then this might be saving a lot of energy. And so what we have here is a device where we have a heavy metal on top of an antiferromagnetic insulator, and we inject from this heavy metal spins into the antiferromagnetic insulator. They are then transported in the antiferromagnetic insulator, and then they're absorbed at the detector, and by the inverse spin Hall effect then read out as a voltage. So this was first pioneered for ferromagnets in the group von Barth van Wees, and there are also some reviews here, and we then did this for antiferromagnetic insulators. And the system that we chose to look at is hematite. Hematite is a uniaxial insulating antiferromagnet where we have two sublattices pointing, say, up or down, c-axis, and we look at different cuts. This is not so important right now, but we can look at different surfaces, so we can have the easy axis perpendicular to the surface or somehow in plane. And so then what we did is we measured the signal as a function of the distance between the injector and the detector. And the surprising finding was we get transport over 80 micrometers. So this was as long as the best ferromagnetic insulators like YIG, but in an anti-ferromagnet. And what we could also see is that actually there seems to be a dependence on the direction and on the field that we apply. So that is not something that is just depending on the material's properties, but there are more things happening. And also what we could see is that there actually is, if you look closely at long distances, an exponential decay, and that shows you that this is really diffusive transport. So we don't see signatures of the predicted superfluid transport because there is no threshold. The temperature is relatively elevated where this works, and you have to measure at long distances in order to see this exponential decay. And previously, people only saw transport in insulators over a few nanometers. The question was why? So to check that, we actually looked at different surfaces and different thicknesses of the sample, and we found that, for instance, C-plane, we have a spin transport that occurs over something like 400 nanometer. At R-plane, we see transport over about 600 nanometers, and then depending on the applied field, we even have the situation where we cannot even fit our system by a single exponential, the decay by a single exponential. So it's not single purely diffusive transport. And the question is, where do all these differences come from? Because fundamentally it's all the same hematite. And so to check where this comes from, what we did is we did imaging of the spin structure, and we found if we have many domains, many domain walls, we get length scale that is very short. If you have domain sizes of a few hundred nanometers, we also get spin transport length scales of a few hundred nanometers. And if you have domains of 50 microns or larger, we get domain transport length scales of a few microns. And if you have many small domains, we get very short spin transport length scale. And this fits nicely a theory paper, which was published here, where due to scattering of the magnons, you have a reduced transport length scale, and so something like magnon domain wall resistance. And so this means by the domain wall, we can govern the spin transport length in these systems. And so just two teasers. Firstly, we can dope these systems to get the transition in this hematite from an easy axis to an easy plane ferromagnet to above room temperature, and we get transport even in the easy plane phase. So there's work by colleagues at MIT and by us showing that we can actually transport above room temperature and in the easy plane phase. And secondly, we also find skyrmion type of structures. So here's the paper if you're interested, and this is now an anti-ferromagnetic anti-skyrmion. So this has the topology of an anti-ferromagnetic anti-skyrmion. If you're interested, look at this paper here in the details. And I think there's a lot more to do with spin orbit effects, also with spin structures. And with that, I summarize also the transport. So we see at the moment only diffusive transport. We can govern the length scale by the domain structure, and there's been a lot of work on transport in the vertical direction that I actually did not have time to go into. Now, the most important slide, so this is the group that has done all the work, because I just get to travel around and give talks, or not travel around, but give talks anyway. In particular, my permanent staff scientist, Martin Jordan, who's driving most of the manganese to gold work, and Gerhard Jakob, who's in charge of most of the oxide work, and Hartmut Zabel, our visiting professor. And we have good collaborations with people in Mainz, at Bessie, at NTNU, in Utrecht, in Japan, Leeds, at MPI, Constance, and in Kyoto, and Grenoble, and at Berlin. And nothing would work without funding. In particular, I acknowledge the IEEE Magnetic Society, as well as our ERC grant and the Norwegian Q-Spin Center. And with that, I summarized. We can read out antiferromagnets by imaging as well as electrically. We can write antiferromagnets, including spin orbit torques and strain, and we can transport information in antiferromagnets over long distances. If you're new to the field, there are a lot of really exciting reviews, so read these reviews here, and then if you're interested in the details, have a look at our work. And with that, I thank you for your attention, and I'm looking forward to the discussion.
Great. Thank you very much for this very interesting talk, Matthias, and thank you very much for staying perfectly on time. As most of you hopefully have seen, we'll be taking questions via the chat. So feel free during this question session to type in whatever questions you may have. So Matthias, the first one comes from Nicolas Reyren. So he asks, what is the main ingredient in determining the domain size in antiferromagnets?
Yeah. That's an excellent question. So we think that one of the things that are important is homogeneity of the material, because even in an anti-ferromagnet, there is no advance in the energy, or no advantage in the energy of forming domains. You have an increase in the exchange energy. So fundamentally, the single domain state should be the preferred state. And this is what we see in these most perfect single crystals here. I think the reason that the domain sizes differ has to do with growth, misfit dislocations. That's one of the things, because due to the strong magnetoelastic coupling, a small change in the crystallographic structure leading to small strain will lead to large anisotropy changes. So that's one of the things. The other thing that we also saw is that some of the surfaces reconstruct differently from others. So this can also play a role in the formation of domains for thin films. For bulk, I think it's simply the quality of the crystal. And there's some nice work from Helen Gomonai, who has shown together with Eric Folven that actually if you have nano-pattern structures, you can get strain relaxation at the edges, leading to some kind of shape anisotropy. So I think, yeah, but I think the answer primarily is the quality of the system if you have unpatterned continuous systems.
Okay, so thanks for that. Are there any questions, other questions? Please feel free to use the chat. In the meanwhile, let me follow up on that perhaps. So you mentioned obviously in anti-ferromagnets, unlike in ferromagnets where the dipole interaction really drives domain formation, there isn't the same kind of mechanism. Mm-hmm. I thought I read somewhere early work that perhaps you can make entropy arguments that you could get domain formation by maximizing the entropy at finite temperatures. And so the question is, have you seen, or is it feasible to kind of study number of domains, domain sizes as a function of temperatures? Is something that you looked at?
Yeah, so that's an extremely valid point. So this is where we did all these studies on the temperature dependence when we go up to the nail temperature. But at least from our experience, it looked like the systems, when they approach the nail temperature, we simply kind of lose contrast before there are like some fluctuations that might increase the number of domains. So I think that's something that very close to the nail temperature might play a role. But I think, at least from what we see, down to the to the temperatures where we see good contrast, the intrinsic pinning of the domains is stronger than the thermal fluctuations. And one of the things that we've been looking at, for instance, is this thermally excited domain wall motion. There's all this theory work from Uli Novak, who's done some really nice predictions that domain walls should move in a thermal gradient, but that somehow turns out to be not so easy to see with high confidence. We have some indications that this exists, but yeah, it's tough because of these inhomogeneities which lead to pinning sites and so on. So I think fundamentally this effect should occur, but we haven't seen it yet. I think that's probably the closest answer I can give to you.
Okay, so a question here from Felix. So what is the nail temperature of the 2D magnet CRPS4, and how do you detect the spin hole magneto resistance?
Yeah, so this is, I think it's 38 Kelvin, something like that, or 48, something, they're all like below 100 Kelvin. This nickel PS3, iron PS3, I think has a bit more, it's like 120 something. Cobalt PS3, chromium PS4, they're all of the order 100 Kelvin or below. And so we measure that by putting platinum on top, and then you go to the spin flop and you see the reorientation. And what is quite crucial is that these systems usually are not very inert, so they start to oxidize at interfaces. So one of the things that is quite important here is that you do the flaking in a glove box and then transfer inside the glove box into the UHV chamber. So we have a UHV chamber which is directly connected to the glove box, so they never see air in between. So initially we had a lot of problems that, in particular, the trihalides, the chromium iodide, the chromium bromide, and to some extent the chromium chloride, you can actually see them turn into green goo while you process them in the lab in air. So that's why it's important that when you do the flaking in the glove box, you, without seeing any air, you immediately put the platinum on top, or palladium or whatever.
Okay, so a question from Oksana. So there aren't too many anti-ferromagnets with higher nail temperature. Is this a problem for applications?
Yes, I agree. But on the other hand, I had a project once on ferro or ferrimagnetic oxidic materials. There's even fewer. There's only magnetite, which has a really high Curie temperature as a ferrimagnet. So for the anti-ferromagnets, there are, you know, a number of systems that have a nail temperature above room temperature, you know, nickel oxide, some of the iron oxides. You know, I would say it's a problem as it is for ferromagnets if you want to look at oxides in particular as well. And of course, for applications, you can only work with systems that have a nail temperature above room temperature. I mean, it turns out one of the key problems for these 2D magnets is that there is only half a system, this iron 5 germanium telluride, which has a Curie temperature above room temperature. And everything of these 2D magnets has low temperature. And the trihalides have like 30, 50, and 60 Kelvin. As I said, the thiophosphates have all below 100 or around 100 Kelvin. Yes, it's a problem. You know, I think there's some scope for working with strain. So there's some predictions if you make these things ultra thin, that by strain you can increase the nail temperature. But let's say nickel oxide with 530 Kelvin, I think we are happy with it. And hematite also has a high, nail temperature above 500 Kelvin. So, you know, I think these 4 devices, this is sufficient. But yes, I think there's a lot of scope for materials engineering. Yes, and you know, in particular for these non-collinear systems, they mostly have low, or many of them have low nail temperatures, and you know, that is not a problem for science, but it's a problem for applications. Yes.
Okay, thanks. Maybe a short last question, if anyone has one. I mean, otherwise I have one, but I'll leave it for the audience if they have one. Okay, so I'll just ask this very quick question. So manganese, you showed some manganese-based anti-ferromagnet.
Mm-hmm.
What about the ones that are traditionally used in exchange biosystems, for example, platinum?
Manganese, iridium, yes. Actually, there is some confidential information that they can also be switched. So I think there was a talk given by someone. So they also work. So there are a couple of problems with these. So one problem is that very often for the exchange bias, you're not using necessarily the collinear phase, but you're using these non-collinear phase. And the problem with non-collinear is, how the heck do you read it out by imaging? So, I mean, all the nice tools I showed you today, and AMR, SMR, XMLD, they work for collinear antiferromagnets. So I think non-collinear antiferromagnets are super exciting, but you need to either have systems like this manganese 3 tin, where you have the symmetry breaking leading to a small moment that gives a large anomalous Hall effect. Or you have to do something else, something smart. But if you have like a fully symmetric triangular lattice, then unless you have atomic resolution, you're lost. So yeah, I think there are a lot of groups working on these antiferromagnets, but we've been working on manganese platinum and iridium manganese, and you have to get the composition pretty correct in order to get a good collinear antiferromagnet. And then the XMLD signal is very small, so they're also tough to image. So very exciting. It's just an experimental problem.
Okay, thanks. So I think thank you once again for this very nice talk, and
thanks everyone.
And so I think we should move on to the next speaker. So a pleasure to introduce Helen Gomanay, who's also at the University of Mainz in Germany, and she has an invited talk on the different mechanisms of the current-induced switching in antiferromagnets. So again, everyone, feel free to think about your questions and ask them via the chat. So the screen is yours, Helen.
Can you hear me? Okay, thank you. First, I would like to say hello, everybody, and I would like to thank organizing this for this very interesting on-site online conference, which is very important in these COVID times. And also, I would like to acknowledge Matthias for his fantastic introduction into antiferromagnetic spintronics. And what I'm going to do now is to fill the gaps which he opened in his talk by discussing different mechanisms of the current-induced switching in antiferromagnets. So the main message of my talk is that the electrical current applied to the antiferromagnetic devices can induce switching through different mechanisms, not only through spin orbit torques, which we could naively think, but also through other mechanisms like thermomagnetoelastic one. But first, I would like to give a very short introduction into antiferromagnetic dynamics. And I start from the slide from Matthias Klaue's presentation, in which he doubted whether the spin transfer torque can effectively act on antiferromagnetic materials. And my answer is yes, it can, it works. And the explanation is related with, is very general, and it's related with spin conservation and spin absorption in antiferromagnetic materials. So let's look at this scheme, which was already shown by Matthias, which shows a collinear antiferromagnet with two opposite magnetic sublattices. And this antiparallel coupling of the magnetic sublattices is kept by extremely strong exchange field of the order of 1000 Tesla. However, if you count a little bit these magnetic sublattices, this immediately induces a very strong exchange torques, which are labeled as gamma X in the slide. And these exchange torques induce very fast antiferromagnetic dynamics. But another important issue of this type of dynamics is that the counting of the magnetic sublattices is associated with creation of non-zero magnetization. Although extremely small, as was mentioned in the previous talk, it's extremely important for the dynamics and description of the antiferromagnetic materials. So magnetization is related with the rotation of the magnetic sublattices. So this means if for some reason the antiferromagnet can absorb the spin, which comes, for example, from the platinum layer, this additional spin creates small magnetization, so it induces counting due to the spin conservation law. And then this non-zero magnetization induces fast magnetic dynamics. This also means that the magnetic dynamics in antiferromagnets can be considered as the dynamics of these small magnetic moments. And the effective equation of motion is in fact the equation of balance for magnetization or spin. So here you see equation of motion for antiferromagnet expressed in terms of the Néel vector n. And this is quite known equation. We will not solve it here. But what is important here is the right-hand side of this equation, which consists of the first term related with the anisotropy field, Hn, and two terms which describe external torques or external forces. And these external torques could be roughly divided in two types. The first one is, in terms of the mechanical system, is the potential force. A good example of such external torque is given by for example, the magnetic field H. So in this case, the external energy depends on the cosine or sine between the squared between the magnetic field and the Néel vector. The other term in the right-hand side is associated with the so-called dissipative force or anti-damping force. And a good example of it is given by spins, currents which are pumped into the system. And the main question which we ask now is whether the electrical current can induce potential or dissipative forces or both, and how it can affect the dynamics of the nail vector. So we start with the dissipative force, because in the experiments, we usually apply current to the platinum electrode, as shown in the left panel. And due to the spin Hall effect, this current can create a spin flux, a vertical spin flux in this figure, which is absorbed by the antiferromagnetic layer. So in this system, electrical current creates a spin orbit torques. And what can be the consequence of these torques? Such torques can induce dynamics of an antiferromagnetic vector. So in the right upper panel, you can see now dynamics of the nail vector, the trajectory of the nail vector on the unit sphere induced by the spin current with the polarization shown with this blue vector. So you see the spin current can induce rotation of the nail vector. As well, the spin current can act on the textures, the domain walls, and it can induce the rotation of the nail vectors and domain wall motion. Spin orbit torques, for sure, can induce very fast dynamics of antiferromagnetic vectors, but these dynamics cannot induce reliable switching, because the dissipative forces do not remove degeneracy between two orthogonal directions of the nail vector, and thus the final state in both cases is unpredictable. However, in the experiments which were already discussed in the previous talk, we see clear evidence of the switching between different states. If you look at the left panel, you see the resistance in a platinum electrode, which is associated with the 90-degree rotation of the nail vector due to the current pulses. So the switching is there, and how can we explain this switching if the current creates only these dissipative torques? So to answer this question, we started to analyze dynamics of the nail vector for different geometries of the spin current, assuming that spin polarization can be directed in different ways with respect to the magnetization. And what we found out is that if the spin polarization is applied perpendicular to the magnetic the lattice magnetization, then the current can effectively work as a field, as a potential force. And this is seen as in the left panel. So the current in this geometry creates torques labeled as T current, which could be exactly compensated by the torques acting from the anisotropy field of the sample. And in this case, the current does not induce rotation or fast dynamics of the nail vector. In contrast, it induces tilting of the nail vector from its initial state, is shown in the right panel. To find the energy, potential energy associated with these torques, we consider the system consisting of two orthogonal domains, A and B, with orthogonal directions of the nail vector. So the movie, which you see now, demonstrates the effect of a spin current on the equilibrium orientation of the nail vectors. The green arrow shows the orientation of spin, and the length of the arrow is associated with the proportional to the current density. So you see that in the domain A, the nail vector is insensitive to the spin pumping, while in the domain B, equilibrium orientation of the Néel vector changes. This is associated with the energy potential, which can be approximated by the expression which you see above. So the current acts on the Néel vector in such a way that the state with the minimal energy is the state with the Néel vector parallel to the current orientation and with n perpendicular to the spin polarization. So we can conclude that current through spin orbit torques can create a potential force which acts on the Néel vector. And in this case, this potential force is a ponderomotive force. It splits degeneracy between the 90-degree domains and induces motion of the domain wall towards the unfavorable domain. So, and induces a reliable switching in a certain direction. So, very nice. This type of switching agrees very well with the experiments made on nickel oxide. So we really observe a switching in the direction with parallel to the current, as can be deduced from the XMLD data. Of course, so you see the circles which demonstrate switching from black to white domains in the right part of the slide, and also in the color figure you see the difference between you see the domains which switch, the regions which switch. Of course, when we worked on this data, we have seen that some of the regions were switched in opposite direction, but we attributed this to the dissipative forces which inevitably were present in this sample. However, we will skip this slide, which is not okay. Sorry, it was some technical problem. However, when we returned back to our experimental data, we have also seen some additional problem, which was also mentioned in the previous talk. So for small current densities, the direction of switching was consistent with the theory prediction. So the Néel vector was switched parallel to the current direction. However, for large current density, the direction of switching was opposite. And it was surprising, but at that moment we were aware of the rocks which claimed that there is some dependence of the platinum resistance versus current, which is related simply by electron migration processes, so some electrical phenomena within the platinum electrode. And these phenomena, of course, can change the whole picture of switching at a high current density. Nevertheless, we decided to check whether the current can really create this potential force on the Néel vector. And for this, we decided to do the straightforward thing. So if the current acts as a field, let's compare the action of the current with the action of the magnetic field, which is well known. So if you apply a magnetic field to an anti-ferromagnetic system, it can induce spin flop. And this spin flop means that if we start from the parallel orientation of the anti-ferromagnetic vector and field, then the Néel vector will be unhappy at some critical field and will try to flip perpendicular to the magnetic field, as can be seen from the left lower panel in the slide. So if we start with a parallel orientation, then at the field around 6 Tesla, the system flips perpendicularly. But when we remove the magnetic field, the Néel vector stay perpendicular to the magnetic field, because it's also equilibrium state of the system. However, if we start initially from the configuration when the Néel vector is perpendicular to the magnetic field, then nothing changes when we switch field up and down, because the Néel vector is always happy in this configuration, as can be seen from the right lower panel of this slide. So what we did, or experimentalists did, we first applied the magnetic field in order to orient the Néel vector in a certain direction, which we know, and then we applied a pulse of the current, and we knew the orientation of the current and the Néel vector for sure. So what we see for one orientation of the current, shown in, with a blue line in the figure, the system shows behavior which is consistent with spin flop behavior induced by the magnetic field. If we apply current in other direction, 90-degree rotated, then nothing happens. So this means that current acts similar to the magnetic field and switch the Néel vector only in one orientation. So one orientation is unstable, the other is stable. Current removes degeneracy between two orientations. But the surprising thing in this case was that for cobalt oxide, in contrast to nickel oxide, the final state of the system was the state in which the Néel vector was perpendicular to the direction of the current. And this switching cannot be explained by spin-orbit torque mechanism, which always predicts orientation of the Néel vector parallel to the current. So it was a challenge, and to find the answer, we look at the other fields which can induce switching of the Néel vector. And what is interesting is that not only magnetic field can induce switching of antiferromagnetic vector, but also stresses can do the same, as was already discussed in the previous talk. And formally, the way the magnetic field acts on the Néel vector, or the energy of Zeeman energy, is very similar to the energy of the strains applied to an antiferromagnet, with only difference that the magnetic field always switch the Néel vector perpendicular to a magnetic field, while the direction of switching, of magnetoelastic switching, depends also on the sign of magnetoelastic constant of the sign of the sample. So we can say, we can look for the magnetoelastic mechanism in our case, but the question is, what is the origin of the strains? And if you look at the energy expression at the second line in this slide, you see that the strains which can remove degeneracy of the antiferromagnetic domains are shear strains. And what can be the origin of these shear strains when we try to switch the system electrically? For this, we should look at the real structure of the device, in which the antiferromagnetic layer is always clamped between the substrate and platinum electrode. And platinum electrode always have very complicated geometry in order to induce reading, writing, and switching. So what happens in a real device? Current which flows from the system has a very high density, and of course it creates some Joule heating losses in the sample. And these Joule heat losses are so pronounced that they can induce temperature variation. And temperature, in turn, can induce volume effects. Then the volume expansion of the crystal lattice. However, thermal expansion per se cannot remove degeneracy of the domains of antiferromagnetic domains because it's isotropic, at least within the plane. So, to have the full picture of the phenomena, we should take into account that the distribution of current and energy and temperature is inhomogeneous, especially in the region in the center of the devices where we observe switching. So, to understand what happens in this area, let's look at the cartoon. It is an exaggerated picture of the temperature distribution, in homogeneous temperature distribution in the antiferromagnetic layer. The temperature induces volume effect, volume expansion, but this volume expansion is larger in the hot regions and smaller in the cold regions, as you can see from the squares in this figure. And this lattice expansion, different lattice expansion, does not fit each other at the interface between cold and hot region. And it can break continuity of strains or lattice of the sample. In other words, this inhomogeneous volume effect induces strain incompatibility of the layer. And this incompatibility can be removed by additional strains. And these additional strains, relative strains, as they denoted here in this slide, are shear strains. So they are anisotropic, as shown by ellipses. And what is also important, this orientation of this strain is different on the other sides of the interface region. So the ellipses at the hot corner are horizontal, and in the cold corner are vertical. So inhomogeneous volume effect can induce strains, shear strains, and the distribution of these shear strains depends on the distribution of the temperature and current in the real sample. So in this slide, I show the summary of thermomagnetoelastic effect, which in fact was first predicted in the paper of Zhang and others. So in the center of the device, the raw strain and temperature gradients, which favor formation of the certain strains exactly in the center of the sample. So you see that within the square, within the dashed square in the left panel, all the ellipses are oriented in the same direction. And this means that the average strain will favor orientation of the Néel vector, which is perpendicular to the orientation of the current. This effect of thermomagnetoelastic coupling can be phenomenologically described with the energy expression as shown below the figure. So the energy, the contribution to the anisotropic energy of the system is proportional to the square of cosine between the current and the Néel vector. And the sign of the effect depends also on the magnetostrictive constant lambda, which can be different in different materials. So in cobalt oxide, the sign of a magnetostrictive constant is consistent with the observed orientation of the Néel vector perpendicular to the current direction, and this explained our experiments quite well. Moreover, we from this by comparison of the energy expression for the magnetic field and current, we can establish field current equivalence in cobalt oxide. So here, left and right panels show the experimental data taken from a simultaneous application of current and field of different values. So you see quite well a linear dependence of between current and field of switching, which is confirmed by the theory equivalence, theoretically predicted equivalence of field and current. And the color code in the left hand side picture shows the probability of the switching phenomenon. However, what is also interesting from in the theory of this thermomagnetoelastic mechanism is that the sign of switching, so this expression of the effective expression of the energy and sign of switching, depends not only on the magnetoelastic constant lambda, which can be different for different materials, but it also depends on the geometry of the electrodes. So in order to disentangle the effects of spin-orbit coupling or electromigration from thermomagnetoelastic mechanism, the easiest way is to compare materials with different magnetoelastic constants and the same material with different geometry of the current flowing through the system. And this what was recently done in our group. So in Matthias' group, with which I collaborate. We return back to nickel oxide, which has opposite, as we assume, opposite magnetoelastic constant compared to cobalt oxide. So in cobalt oxide, we see switching of the Néel vector to a perpendicular orientation to the current. So what we can see in the nickel oxide, initially we have seen switching parallel to the current, but then we decided to try different geometries of the current and see whether we can manipulate the direction of switching. In this slide, you can see two different geometries in upper and lower rows. So in upper row, the current flows straight from left to right electrode, and it creates a strain distribution, which is shown in the center panel by color codes. And this distribution of current, strain, and whatever it is, induces a switching as shown from left and right panels to the state in which the Néel vector is parallel to the current direction, which is consistent with both models, model based on spin-orbit torques and a thermomagnetoelastic mechanism. However, if we change the geometry of the electrodes and we apply current which flows a 90 degree, as shown in the lower panel. Then the distribution of strains is quite different compared to the strain, to the upper slide. But the direction of the current in the central region is the same. And in this case, we see switching of the near vector, which is perpendicular to the current direction. This type of switching is consistent with a thermomagnetoelastic mechanism, but could not be explained by spin-orbit torques. To have more evidence of a thermomagnetoelastic mechanism, we tried to eliminate the direct effect of spin-orbit torques on the switching. And for this, we made a special design of the platinum electrodes, which had a hole in the center of the sample, so that the current flow only around this hole and does not produce any direct spin-orbit torques on the central region of the sample. Nevertheless, in this case, we still see switching depending on the direction of the current. We see 90 degree switching, which is fully consistent with a thermomagnetoelastic mechanism and could not be explained by other theories, at least known to us. This was the switching, which shows the initial and final state of the system. So we see that the strain removes degeneracy of the domains and stabilize the final state of the material. However, the question is how the dynamics of this switching looks like. And for this, we also tried to simulate the dynamics of switching using the equation of motion for the anti-ferromagnetic vector in presence of magnetoelastic interactions induced by the current. So we started from the domain, 90 degree domain shown with the blue ellipse in the central figure, which simulates the experimental situation, and arrows here show the direction of the near vector. So now I will show the video how the system change its state when you apply a strain field which is consistent with the distribution of the current induced strains. So you see that the process starts from the edges of the samples, and then the system switch 90 degree, which is very similar to what you really see in the experiments. In the simulation, we also see 180 degree domain walls seen as a thin blue lines in the pink region. We do not see these lines in the experiment, but we can attribute it, these 180 degree domain walls to the boundary conditions used in the simulations. With this, I'm at the end of my talk, and to conclude, we demonstrate that the current induced switching can involve more mechanisms, as we assumed before. The current in platinum creates not only direct spin orbit torques which can induce switching, but it also creates a very complicated system which involves magnetoelastic interactions. And this makes physics much more complicated, but opens a way to manipulate and optimize a switching by proper tailoring of the devices and electrodes. And also we demonstrated that the action of the current is equivalent to the field, and we even know the exact numerical relation between field and current for the case of cobalt oxide. With this, I would like to acknowledge the collaboration between our group headed by Sinova and experimental group of Matthias Klaue. And especially I would like to acknowledge Lorenzo Baldrati, who was in charge of all these experiments which I demonstrated here, and he was a generator of these very nice ideas. And I would like also acknowledge Henrik Meyer, whose picture I haven't found in internet, but I can suspect that somewhere between these masked people, he is also present. So with this, I end my talk, and thank you for your attention.
Thank you very much, Helen, for this nice talk. So we're running a little behind on the timing. We still have time for questions. So please, those in the audience, if you have questions, please use the chat, type in your question, and I'll read it out if there are any. Okay, so I have one from Oksana. So for large current densities, there will be a large increase in the temperature. So are there any other thermal effects that could play a significant role? For example, thermal dependence of magnetic anisotropy, or thermal activation over energy barriers?
Can you repeat the last sentence, because I haven't heard you well. Can you speak a little bit up?
So, so the question is regarding increased thermal effects with large currents. So could other effects such as a temperature dependence on the magnetic anisotropy, or thermal activation over energy barriers, these kinds of processes play a role? Have you considered this?
Oh, thank you for this question. Of course, when you heat the sample, then you not only create these magnetoelastic profiles of anisotropy, you also change. You can also change the value of the magnetic anisotropy itself. And for example, for hematite, it can be extremely important because in hematite the anisotropy energy is very sensitive to temperature, and you can even go from one phase, magnetic phase, to the other. However, in nickel oxide and cobalt oxide, the temperature, the magnetic anisotropy is much more robust to the temperature effect, and on the other hand, magnetoelastic properties are extremely strong. So these two materials are known for their large magnetorestrictive constants. So I think that in any case, it's a balance between the pure magnetic anisotropy of the sample and contribution from the magnetoelastic effects. But I think this can be extremely interesting because we can find much more new phenomena which we can have only from spin orbit switching.
Yeah, definitely. Okay, thanks for your answer. So are there any, maybe we have time for one very short question if there is one from the audience? No. So let me just maybe very short question and a short answer. So you looked at the dynamics of the nail vector exclusively in what you described. Do you think it's important to take into account the M vector for any of these processes? So the sum of the moments and not the difference.
can you, I'm sorry again, it's the
Yeah, so just
sound.
quickly, so the M, so did you neglected the total magnetization dynamics in all of this. Do you think this is something that can be neglected completely, or?
No. This is the main point of all this anti-ferromagnetic dynamics is that in order to have dynamics, you need to induce canting of magnetic sublattices. So effectively, this canting is extremely small. And because it's small, this allows us to exclude the magnetization from the equation of motion. So we can get these effective equations in terms of the Néel vector. But you cannot exclude a magnetization fully, because otherwise the system will not rotate at all.
Yeah, okay, thanks. So, so in the interest of time, let's move on. So thank you very much, Ellen, again, for this very nice talk. So our next speaker in the session, which is another invited talk, is Saul Venez at the ETH Zurich in Switzerland. And his talk will be on the interface-induced chiral magnetism and current-driven wall motion in ferromagnetic insulators. So now the screen is yours.
I would like to thank the organizers for giving me the opportunity to present here some of my work, and also for making possible this online version of the conference. So today I will show how we can use spin currents to prove the surface magnetization of magnetic insulators, and how to excite magnons and detect them electrically in non-local geometry, as the one I shown here. And last but not least, I will show how we can use spin currents to switch the magnetization of magnetic insulators and drive domain walls along a racetrack memory device. So that to start with, so how we generate the spin currents in all devices. So we use the spin Hall effect, which basically exploits the spin orbit coupling of materials to generate the spin currents. So in a material such as platinum, so when we run a current through it, you generate a transverse spin current. So the efficiency of this effect is given by the spin Hall angle, and by reciprocal process, you generate from a spin current, generate a charge current. This allows an efficient way of generating spin currents and also detect them in devices. And in particular interest for us is that we want to use these spin currents to manipulate or make a possible spintronic devices made of magnetic insulators, in which charge currents cannot flow in the magnetic insulator, but spin currents can be injected through the interface with a magnetic insulator. So, but the question is why we would like to work with magnetic insulators. And the first thing that we have to think about is that we have many materials, such as garnets, in which the damping is very low, so comparable to permalloy. And if you think about comparing with cobalt, the damping is much lower in these materials. So meaning that the dissipation in such devices would be much smaller. So also these materials, because they exhibit very low damping, they can also enable new functionalities, because also they are insulating. And this, for instance, is the propagation of spin waves, in which you can electrically excite and propagate spin information in the form of spin waves in the material. But also these materials, they have plenty of those that exhibit ferrimagnetic or anti-ferromagnetic order, meaning that the different sublattices in the material, they couple anti-ferromagnetically, and the net magnetic moment is lower than in ferromagnets. And this is useful for spintronic devices, because the dynamics you can induce in these systems are much faster. For instance, in domain wall motion, you can drive domain walls much faster, because the magnetic moment is reduced. But apart from that, you can also tune the magnetic properties, or tune the properties of the materials by chemical composition and growth. So that's why we would like to work with the magnetic insulators. So there have been several realizations of spintonic devices using magnetic insulators coupled to heavy metal layers. For instance, by exciting the ferromagnetic resonance of a magnetic insulator, you can pump spins in a heavy metal layer. You can detect them by the inverse pinhole effect. So you can also excite spin currents through the interface by applying a transverse thermal gradient across the interface. So topics that we are interested is in the Magnon spin transport, in which you can excite electrically, you can excite Magnons in the magnetic insulator, and you can detect them in non-local geometry. So also these type of heterostructures, when you have a heavy metal coupled to magnetic insulator, you have a type of magnetoresistance effects. It's called the spin Hall magnetoresistance, which is related to the relative orientation between the spins and the magnetic moments in the magnetic insulator. And this leads to magnetotransport effects that allows us to read the surface magnetization of magnetic insulators. So also has been shown that you can exert torques on the magnetic insulator, and for large driving currents, you can even switch the magnetization of this magnetic layer. So you can manipulate the magnetization. And last, that's what I also talk to you today, is that you can, in these heterostructures, you can stabilize homochiral domain walls and drive them by charge currents. So this is the outline of my talk. So in the first part, I will show you how we can use this spin Hall magnetoresistance to read the surface magnetization of magnetic insulators. In particular, we'll develop to then explain how this spin transport across the interface occurs in microscopically related to the all properties of the interface, and how we use this to prove the magnetization of a low-dimensional magnet that doesn't exhibit a long-range ferromagnetic order. So also I will show you that, that in non-local structures, as the one shown here, you can electrically excite and thermally excite as well Magnon currents and detect them non-locally. And I will show you that the diffusion length of these Magnons depend on the excitation mechanism. And in the last part, I will show you that we can switch the magnetization locally in a magnetic insulator by having a platinum on top of the magnetic insulator platinum line. And also this same platinum line can stabilize homochiral domain walls and drive them by charge currents. So in the first part, basically when we have a spin Hall effect and a spin Hall effect in a heavy metal layers, if you put both effects together, what happens is that you have an additional charge current generated because of the combination of the charge to spin and spin to charge current. So this additional current leads to a reduction of the resistance of the material, but this amount that relates on the spin transport properties of the material as well as on the thickness of the heavy metal layer. So now if you put this material next to magnetic insulator, now what happens is that you read the different resistance depending on the relative orientation between the spins and the magnetic moments, because in this configuration, in the first approximation, you could think that there is a reflection and there is no actual absorption of these spins in the magnetic insulator. But when the configuration is perpendicular, there's an absorption, and thus there is a reduction of this additional charge current, and this leads to a high resistance state. So this is demonstrated here in platinum on top of yttrium iron garnet, in which you can see that depending on the direction of the magnetic moments, here would be perpendicular to the spins, you have a high resistance state, and when they are parallel, you have a low resistance state. So the amplitude of this effect is given by this formula. So in the first approximation, you just consider this parameter here. This is the real part of the spin mixing conductance. And this was initially, this effect was initially used as a fictive tool to characterize the spin transport properties and the interface quality of different heterostructures. But last but not least, that we can also use this tool as a way to prove the surface magnetization of magnetic insulators. For instance, by tracking this field dependence, you can see which magnetic field you have a saturation, and also if resistance evolves, and will also gives us information whether you have some, for instance, some paramagnetic contribution. So this is a summary of some of the works that we performed over the last years, and I will talk in particular on the exploration of this effect to detect the magnetization of a low-dimensional ferromagnetic material. So what the question is that the spin-hole magnetoresistance theory was essentially made of phenomenologically. So and also then typically it's only considered the real part of the spin mixing conductance. So now if you think about the spin transport across the interface, so you have three components in the spin conductivity across the interface. So the first term here, it relates to the excitation of Magnons in the magnetic insulator. So the second term is what is called because of the symmetry is would be equivalent to the damping-like torque on the magnetic insulator. So and the third term is the field-like torque. So in most systems, so this part was neglected initially in the spin-hole magnetoresistance theory, and in most systems, it was found that the spin mixing conductance, the real part of spin mixing conductance, was dominating over the field-like, but it was not addressed why this could be in a device. So in collaboration with Professor Bergeret and Dr. Golovac, we addressed the microscopic origin of these components, and we found explicit equations that relate the spin mixing conductance to the interface properties of the material. So actually, we have the density of states of the non-magnetic metal. So we also have this SSD exchange coupling at the interface, and also the surface magnetism of the magnetic insulator. And these parameters here relate to the magnetic moments of the systems, either parallel or perpendicular to the magnetic field applied. So importantly, so these equations allows us to explain that the spin transport properties across interfaces with systems that doesn't exhibit or exhibit any type of magnetic ordering, for instance, anti-ferromagnets or even paramagnets. So, so also we developed equations for analytical equations taking into account these contributions. And also this important is this term here that, for instance, at high temperatures, or for instance, across a ferromagnetic transition, you could excite a lot of Magnons in the system, and this was not taken into account initially, although now it's quite clear that also the excitation of Magnons in the magnetic insulator contribute to the local magnetoresistance in the heavy metal magnetic insulator bilayers. So we applied this theory to investigate this heterostructure that I'm showing here. Basically, we have a lanthanum cobaltite coupled with platinum. This magnetic insulator at low temperatures, and has an ordering temperature, so the Curie temperature at 85 Kelvin. And with a small magnetic field, you can saturate the magnetic moments of the relatively low magnetic field, you can saturate the magnetic moments. So now, if you analyze this heterostructure, what we see is that we have a depletion of cobalt in this layer, and then we have a surface, rich surface on cobalt rich surface that we want to investigate by measuring the resistance in the platinum layer, as also has been explained before by Professor Chloe. So the idea is that we measure now at high temperatures above the transition, the null temperature of the system. So we measure the resistance, and we see that this exhibits the Hanle magnetoresistance. So basically what we observe is that we have an increase of the resistance when the magnetic field is applied perpendicular to the spins. And this is related to the spin precession of the spin generated in the magnetic layer, and this is the effect that is intrinsic of the heavy metal. So now when we apply parallel to the spins, there is no change because you cannot make the spins to precess. So now the question is now if we measure at lower temperature, below the Curie temperature, we observe that we have an additional magnetoresistance along the y direction, and this is directly the spin Hall magnetoresistance, because the Hall magnetoresistance cannot lead to this magnetotransport. So now there should be some magnetic moments aligning towards this direction, and there is some change with respect to a zero field. But importantly here is that we don't see a saturation up to 9 Teslas, telling us that there is no correlation between the bulk properties of this film and what we measure in the surface. So actually we track this amplitude as a function of temperature. We see that there is no correlation with the transition temperature of the film. And we see that this surface behaves as a paramagnetic-like surface. So what we did was to use the theory that I explained before and also model the surface as responding as a superparamagnetic system, as well as a low-dimensional ferromagnetic system. And what we could do is we could get nice fits of the magnetotransport in the system, and be from the fits of the superparamagnetic system and different models of two-dimensional, one-dimensional material, we see that we can fit, we can qualitatively explain the temperature dependence of this magnetotransport in the system as related to the surface behaving as a low-dimensional ferromagnet. So in the second part, I would like to show you that we can excite magnons and detect them by electrical means. So now, considering again the spin Hall effect, now when we have the spins that are parallel to the magnetic moment, so we can excite magnons. We can either create or annihilate magnons in the magnetic insulator, but also we can absorb them and detect them by charge currents. So how does it work? So basically, we have now a platinum layer on top of the magnetic insulator. So we can excite magnons by applying a charge current. If we have the magnetic moment basically oriented in parallel to the spins, and the propagation of these magnons can be detected non-locally in another stripe, platinum stripe, by having the opposite effect here. So we convert magnons to spin and the spin to charge current by using the inverse spin Hall effect. So now we have to think also that we have a thermal gradient across an interface between a magnetic insulator and the heavy metal. So we can also drive spin currents to the heavy metal layer and magnon currents in the magnetic insulator. So now you forget about the spins. When you run a current, you also heat up your system, and this thermal gradient also generates a magnon current, and you can detect this magnon current by the same means by measuring the inverse spin Hall effect. So the devices that we investigated are the ones shown here. So we have very thin layers and very narrow layers, and we make devices with different distances and inject current and measure the non-local resistance on this platinum stripe on top of the yttrium iron garnet. So you can decouple the electrically and thermally excited magnons by measuring the first and second harmonic response of the signal. Also, the angular dependencies also relate to the fact that for the electrically excited magnons, we have both the spin Hall effect and inverse spin Hall effect involved, and this leads to a sine square dependence with angle on the response of the magnon current that we detect in this stripe when we inject the current here. So that when we measure the second harmonic, we can detect the thermal magnons, and this leads to a sine phi dependence, because only the inverse spin Hall effect the detector is involved in the detection process. So now I'm measuring these signal as a function of different distance. You can track the Magnon transport, and you can extract the diffusion length of these of the Magnon conduction in the system. So here I'm showing a particular case of 150 Kelvin. So comparing electrical and thermal Magnon excitation, and by measuring the decay length of in the exponential regime, we can extract the Magnon diffusion length. And we do so at different magnetic fields and at different temperatures. What we observe is that we have a different Magnon diffusion length for electrical excited Magnons with respect to the thermal ones. And also we observe a large field dependence. So this together tells us that we excite different Magnon distributions when we excite electrically, or when we excite thermally. We excite different Magnon contributions, and these Magnons contribute differently to the Magnon transport. So in the and second is that then because of this field dependence, strongest field dependence, it tells us that there should be a domination. So dominating subthermal Magnons dominate the Magnon transport. So interestingly, we also observe that when we compare our results on thermal excitation with the ones in the literature for other jig thicknesses, or even different fabrication methods of the yttrium iron garnet and different thicknesses, we observe that the Magnon conductivity is the same, which means that the thermal Magnon transport is a universal effect that doesn't depend on fine details of the growth conditions of the yttrium iron garnet or even the thickness. So with this, I would like to summarize the first two parts by saying that the spin-Hall magnetoresistance is an efficient way of detecting the surface magnetization of magnetic insulators, and we provide a microscopic description of the spin transport across interfaces, and used this magnetotransport effect to explain or to analyze the surface magnetization of a low dimensional ferromagnet. And I also show you that we can excite electrically, by electrical means, we can excite both electrical and thermal Magnons in yttrium iron garnet, and we show that we have different propagation lengths depending on the way we excite the Magnons, and that the low frequency Magnons, so the ones that are in the gigahertz regime, dominate the Magnonic transport in the system, even at high temperatures where the excitation should be more in the terahertz regime, and that's because of the fast relaxation of the Magnons generated in the system. So in the last part, I would like to show you that we can locally switch the magnetization and also drive domain walls in magnetic insulator. So why we would like to drive domain walls? And essentially, if you think about so our current memory technologies, so for instance the hard disk, so we have the magnetic elements are stored in a surface, and also we have reading elements that have to mechanically move over the surface, meaning that we have a limitation in the capacity, the memory capacity, as well on the reading capabilities of the system, because you have to mechanically move a red head along the surface. So now if you think about the information stored in pillars, you can drive them by charge currents. Having also injectors and detectors that are fixed, you can speed up the reading and of the information, as well as increase the capacity, memory capacity, because you can naturally go to the third dimension. So this is the most promising layout for realizing these kind of domain walls, and how these domain wall racetracks work. So essentially we have three ingredients. The first, that we need is to have a perpendicular magnetic anisotropy and the Zielinski-Morier interaction, which allows us to basically break the symmetry and stabilize homochiral domain walls. And this is very important because the sign of the torques depends on the chirality of the layers. And also, so we need to use a spin orbit torques to drive the domain walls. So then these two spin orbit torques and the DMI can be brought to the system by using the platinum line. So the same material that is used for generating spin currents also induces a strong DMI that is capable to stabilize these domain walls. And importantly, they are chiral because the interaction is set by the material that you bring into the system. So this type of structure allows you to apply charge currents to the material, and then by the spin current generated, exert a torque that is the chiral dependent on the chirality of the domain wall, and then drive all the main walls along the same direction as long as they have the same chirality. So what are the limitations of these racetrack memories? So the first that we have to think is that in ferromagnets, you have stray fields which limit the domain wall velocity. But this can be suppressed, for instance, with synthetic anti-ferromagnets, in which then, because of this, the absence of these stray fields, now you can drive domain walls much faster. So by the time that this was done, so it was increased by a factor 2-3 the domain wall velocity. And you can also do this with ferrimagnets. So when you move away from the angular momentum compensation temperature, so the system becomes more ferromagnetic, and then the domain wall velocity is be limited by the fact that you have stray fields. But when you go to the angular momentum compensation, then you get a higher velocity in the system, and it was even demonstrated that you can move domain walls above 1 kilometer per second. But another limitation is the fact that you have pinning, you have defects in the system, and this prevents you to drive domain walls at moderate charge currents. So we moved to the use of rare earth magnetic insulating garnets because these materials exhibit low damping and also have ferromagnetic order, which are the properties that we would like to have to drive domain walls at very high speeds, but also bring additional functionalities. I'll show you that you can also excite and Magnon currents in the device. And it was also shown that you can excite, you can drive large torques in the magnetic insulator and switch the magnetization. So now the question is whether we can stabilize homochiral domain walls in the magnetic insulator as well, and if we can drive them by spin currents. And the answer is yes, and that's what I'm going to show you. That basically our devices are made on substituted gadolinium gallium garnet. By pulseless deposition, we deposit thulium iron garnet, and then we in situ deposit platinum to have a best interface possible, and we pattern these layers in this device structure, in which you have racetrack with a whole bar contacts to measure also electrically the magnetization in the system. For instance, here, if we run a current in this direction and we measure the whole response, we can measure the magnetic orientation of the system, and this shows that by sweeping the magnetic field out of plane, this exhibits a perpendicular magnetic anisotropy, which also is a property that we need to realize these domain wall racetracks. So now if you apply a magnetic field in the plane and you run a large driving current, so if you send pulses, you exert torques to the magnetization of the magnetic insulators, thulium iron garnet, and you can eventually switch the magnetization. This is what I'm showing here, that if you apply a magnetic field in this direction, so you break the symmetry of the system and then stabilize one of the, either stabilize up for positive current pulses and down for negative current pulses because of the symmetry of the effect. Now, if we revert the orientation of the magnetic field applied in plane, now we can stabilize up domain walls by sending current pulses with negative polarity and down magnetization by applying positive current pulses. So this tells us that we can control the final state of the magnetic system by either applying current pulses and magnetic field in plane, and when they are parallel, so we stabilize up magnetization, and when they are anti-parallel, and this stabilize down magnetization. This simply because of the symmetry of the damping like torque in this heterostructure. But the question is how this switching occurs, because when we send a current pulse, we see a magnetization switch in the region only, because that's the part that you can read out in electrical measurements. But now we want to see how this switching occurs in the system, because now we have to think also that we only etch the platinum and the thulium iron garnet is continuous. So this is a differential Mock image that is sensitive to the out-of-plane magnetization. So that's in the differential mode. We first saturate down the magnetization, then we send a current pulse, and we see that we switch the magnetization only in the current line, telling us that we can control locally the magnetization in continuous magnetic fields, which could be interesting, for instance, for magnonic applications. So we now measure the chirality of these domain walls by using a nitrogen vacancy magnetometer. Basically, we have a defect placed at the apex of a diamond tip, and we measure the stray field in a domain wall when we have a part that is partially covered with platinum, a part that is not covered with platinum. So this is the stray field map that we record, and now by fitting the stray field to the expected domain wall, different domain walls that we could have, which would be blocked for a system in which we don't have a Zarinsky-Maury interaction, and with respect to the left and right domain walls where we have Zarinsky-Maury interaction. In the part that we only have thulium iron garnet with no platinum on top, we observe that the domain walls are left-handed Nel. And when we have platinum on top, we partially quench this chirality because of the positive AMI. So in conclusion, with these measurements, we observe that we must have a Zarinsky-Maury interaction at the interface between the thulium iron garnet and the substituted gallium garnet substrate. And on top of that, we also have Zarinsky-Maury interaction for the platinum layer on top, which partially quench this DMI because the contribution of that interface opposes the one of the substrate. But still, we could drive domain walls, as I'm showing here. So basically, if we have a domain as the one shown here, we can apply a pulse, and we can drive domain walls from left to right by measuring the displacement as a function of the pulse length. So we can extract the domain wall velocity. If we do this for different magnetic fields, we see a linear trend as expected. And when we measure for the other configuration with magnetic field and current, we see that we have a shift, telling us that this shift is related to the internal Zarinsky-Maury interaction that we still have in this system that is partially quenched with the platinum on top layer. So basically here I'm showing the domain wall structure that we expect. So we have a partial Nel chirality because of the internal DMI in the system. Now when we set the magnetic field, we either help the domain wall to be stabilized or we set the chirality to oppose to the original one because of the DMI. That's why we observe here this shift. So basically from this we can measure the DMI, and we can say that we can control the domain wall propagation by controlling the direction of the current, of the magnetic field, and the DMI in the heterostructure. And last, I'm showing here that the domain wall velocity, we can drive domain walls at very moderate or quite low current densities, in which typically magnetic ferromagnetic layers such as cobalt or cobalt iron boron. You cannot drive the main walls. We can drive them at in the range of 100 or 200 meters per second, which tells us that these materials are ideal for racetrack memories. And with this, I would like to conclude and say that we show you that we can switch the magnetization in magnetic insulators in continuous films locally, which could be interesting for instance, magnetic application, which you can think about patterning retiring magnetic landscapes by applying charge currents in this system, and then you could, for instance, check how the Magnon currents propagate through these magnetic landscapes. So I also showed you that we have interfacial Emi that comes from both the substrate and the polymer and as well as from the coupling with the heavy metal layer. This allows us to stabilize chiral domain walls, for instance, only by using oxide-oxide interfaces. And last but not least, I also show you that we can drive domain walls at quite a high speed, and also this has been confirmed with other works, such as the one I'm citing here. With this, I would like to thank all the people that contributed to this work, so which basically in the first two parts was mostly done with collaboration with people in Anogune, and also with people in TTH, which belongs to the last part of the talk. And with this, I would like to thank you also for your attention.
Great, thank you very much, Zan, for this very interesting talk. We are open for questions, so please use the chat. So the first question I have is from Helen Gomanay. So she would like to know, how do you estimate the wavelength of the magnons that you excite, which contribute to the signal that you measure?
Yes. So we measure the signal. So I'm trying to, yeah. So we measure the signal as a function of, so for different devices. So basically, yeah, we measure the decay as a function of for different for devices of different distance between the injector and detector, and by measuring the decay, so we see that in the short range regime, so we have a diffusion regime, and we measure in the region in which we have a single exponential decay, and from this we can then detect the magnons, the Magnon diffusion length.
Okay, thanks. So I have a question here from Oksana. So she would like to know, how can you explain the dependence of the Magnon diffusion length on the excitation method? Shouldn't this be a material property, an intrinsic material property?
Yeah. So the first thing is that it is known that while for the case of electrical excitation, it's believed to be only dependent on one decay length. So now there are several papers that show that you have two decay lengths for the thermal excitation. So that what is known is that that the high frequency magnons decay quickly to the low frequency magnons because they propagate much less. But the idea is that what we infer from these measurements is that we could excite different propagation, so different distribution of magnons depending on whether we excite the system by spin torque. So electrical means spin torque, or thermally. That's what we concluded with these experiments.
Okay. I have a question here from Nicola Reyren. So we'd like to know, do you understand, or how does one understand the mechanism for the interfacial DMI in these insulating materials? So presumably on the last system that you mentioned.
Yeah. So yeah, the mechanism is different than in metal because you don't have electron conducting in the system. So it must be a super exchange. But the question is still if it's directly an interfacial effect, or could be that we have, for instance, there are now also reports that show that you could have some gradient in the composition across the interface. So it's still work for theoreticians to show that you can actually get this interfacial DMI. I can also mention that this interfacial DMI, it's orders of magnitude smaller than what you get in metal-metal interfaces. So it's not surprising that you could get interfacial DMI in this kind of system, but it's not yet theoretically addressed. So we could also say that, that because in the systems that we explore and exhibit ferrimagnetic order, or even in anti-ferromagnets, so with a very small DMI, even you have 2 orders of magnitude smaller than in metal-metal interfaces, you can stabilize chiral domain walls.
Okay, thanks. And so just a follow-up from your first question from Helen on the Magnon wavelength. So I believe the answer is that if you, from the diffusion lengths, you can deduce what the Magnon wavelengths, typically Magnon wavelengths that you excite. Is this something that you can confirm? She was wondering about what wavelengths are excited.
So exactly. So you not excite just a single. So that would be. I mean, you should make resonance experiments to just prove one wavelength. But the idea is that you cannot avoid to generate different distribution. And the question is that only so the low frequency magnons are the ones that propagate to much longer distances. And what you measure is the average of all distribution. So you don't measure only a single, say a single magnon with a very narrow frequency range. You excite a distribution, and what you measure is the average of this distribution. That's what you detect in the experiment.
There are some follow-up questions, but I think in the interest of time, we should perhaps move on, or perhaps you can answer directly in the chat later on. So let me thank you on behalf of everyone once again for this very interesting talk. So
thank you.
So we now move on to our contributor talk. So the first one is from Jaroda Slavinska from the University of Groningen. And so her talk will be on the spin Hall effects in ferroelectric Rajba semiconductor germanium telluride. So this is 15 minutes plus 5 minutes of questions. So the screen is yours.
Okay, thank you for the intro. Can you hear me? Okay, thank you for the introduction. And I would also like to thank the organizers for professional handling of this conference in these unusual circumstances. So in more detail, I will be talking about ferroelectric control of spin-to-charge conversion in germanium telluride. The choice of material here is quite important, so I will also try to present as broadly as possible the properties of this material and the related challenges. So, germanium telluride is a prototype ferroelectric Rajba semiconductor. I will explain this concept in a bit more detail in a second. Then I will move to the issue or the challenge of ferroelectric switching in germanium telluride. And then I will show how this concept can be used for ferroelectric switching of spin-to-charge conversion. So it will be combining like ferroelectricity with spintronics. But anyways, before I start, I would like to mention all the people involved in this work. So I do the theoretical part with the collaborators from UNT in US and with CNR Spin in Italy. But here I would say that experimental part is of fundamental importance So I mean, I have to mention the efforts of all experimental groups involved. Well, the whole research was coordinated by the team of Cristian Rinaldi and Riccardo Bertacco from Politecnico di Milano. Okay, so ferroelectric Rajba semiconductors were proposed a couple of years ago, theoretically. The concept itself, it's not so complicated. What we have here, we have ferroelectric, so we have a polar distortion, which intrinsically breaks the inversion symmetry in this material. And due to the symmetry breaking, we have splitting of the bands. In germanium telluride, the splitting is quite large. Of course, we also have spin texture. And what is really interesting about this material is that when we switch to the opposite distortion, for example, by applying the electric field along this axis, we also can switch the spin texture. So we have the link between the polar degrees of freedom and spin degrees of freedom. Here, for the sake of completeness, I also show a constant energy cut. So, I mean, basically, these are the same bands as here. I just wanted to show this characteristic shape and circulation of spin texture of each band. One is clockwise, one counterclockwise. Okay, so what we can have, how we can use this concept, this idea. It can be useful, for example, here I have shown a simple model of spin transistor. We could, for example, use electric field to switch the states in the spin channels to manipulate the spins in the channels. Also, the relevant thing here is that germanium telluride is practically always ferroelectric in the sense that Curie temperature is very high. So this shows like a perspective of room temperature applications, especially in connection with large splitting. But okay, this is theory. This switching of spin texture, it's not so trivial from the experimental point of view. So we have some achievements also in this field. So the colleagues who work on experiment performed RPS studies. So they managed to visualize these bulk bands that I have shown in the previous slide. And they have also performed spin RPS for these bands and actually demonstrated that for 2 samples with opposite polarization, we indeed have the reversed spin texture. So they sort of demonstrated the link between electric dipole and spin texture. Okay, but let's come back to theory. Here we have an important question. Okay, since we have ferroelectric switching of spin texture, maybe we could also switch spin to charge conversion. So use like analogous concept. Then we try to investigate whether spin to charge conversion could be observed in this material. So, for example, it has Rajba bands, so it could reveal, in principle, Rajba-Edelstein effect, or spin Hall effect, which can occur in any material with sufficiently large concentration of charge carriers and with large spin orbit coupling. But again, here it leads us to a kind of contradiction, because for sure, spin Hall effect in a trivial semiconductor requires doping, and there's a question if this doping will not ruin us the ferroelectricity. So this is a question whether ferroelectricity is not forbidden in case we dope the system. So let's take a more careful look on this issue. spin hole conductivity can be easily calculated. It is quite easy to implement Kubo's formula. And here we have 10 non-zero components of spin hole conductivity based on the space group and symmetry of this material. 4 of them are independent, so I plotted them here. But as I mentioned just a second ago, here we don't have any states for zero chemical potential. So we have to tune this chemical potential to reach some non-zero spin hole conductivity. So it is also not so difficult to include in the calculations the doping. And of course, we can calculate in the same way spin hole effect for doped systems. Here I have presented the results of spin hole angle calculated for germanium telluride doped with different concentration, for example, in the range of 10 to 20 holes per cube centimeters or larger, 10 to 21. Actually, this one is closer to experiment. And it is easy to notice that actually the spin hole angle is close to the one of platinum. So it looks quite promising. But what else we have noticed here is that we noticed that we also observe a similar spin hole angle for ferroelectric structure. So then it brings us to a second question, whether this ferroelectricity matters. So it's not only the question whether we can have ferroelectricity, but also to the question whether we can use it for anything. So, okay, so we have, so first question is whether the polar distortions will survive. If we have a concentration of charge carriers, it should lead to quenching of polar distortion. Germanium telluride is p-type doped. Again, we took it into account explicitly, and actually we demonstrated that the polar distortion will decrease very slowly. So the concentration, the charge concentration, Hall's concentration that would remove the distortion would need to be of the order of 10 to 21, which is like an order of magnitude more than we have for the experimental samples. The interesting thing is that if we have n-type doping, the polar distortion doesn't disappear at all. So probably this is also an interesting direction to study. So for germanium telluride, indeed, we can maintain this polar distortion. It is related to a detailed mechanism of ferroelectricity and the lone pairs, which are the fundamental, I mean, it's a fundamental mechanism between the behind the ferroelectricity. This is an important detail, but what is even more important is the question whether these free charge carriers that come from doping will not screen the external electric field. So here I present a piece of experimental result. I will not go into details at all because it's definitely non-trivial, but our colleagues managed to show that the ferroelectric switching is indeed possible, and they did it quite recently. Okay, so this ferroelectric switching can be used not only to switch the spin texture, it can be also used for ferroelectric control of spin to charge conversion. So here on the left, I present it's one experimental setup and just two views to facilitate the explanations. So here in the upper panel, I show how it actually looks. So germanium telluride is embedded between iron and silicon. We have the polarization, electric polarization perpendicular to the sample. and we can change the ferroelectric state. Then it's still the same interface, just a sketch is a bit different because this sketch should illustrate the spin pumping experiment. So here we can inject the spin current into germanium telluride and by spin to charge conversion generate electric current which is in plane, so perpendicular to the spin current. So what is the most relevant here, that we actually, when we change the ferroelectric state, we can reverse the sign of spin to charge conversion. This is very fundamental and important, useful for applications. It agrees also well with experimental results, but I may say that not only experiments were extremely complex, also the calculations here were quite tricky because in principle you cannot obtain this picture while using periodic boundary conditions. So there was a
We lost your connection briefly there, Jagoda. I cannot have any, I don't have any sound.
there was some sort of interruption. I don't know
I
what
think
happened. I don't know. I'm sorry for that. Anyways, I was here. I was trying to explain that the origin of this switching, that this is related to electric charges here on the borders of the interface and the electric field inside. And this is a mechanism that changes the band structure. So it's actually the change of the bands rather than change of the spin texture that contributes to this switching that we can see here and that was observed experimentally. And also we have obtained a perfect agreement with experiments. So again, spin Hall angle is around 1%. Okay, so let me briefly summarize. I actually have shown the most important results in the last slide. So the ferroelectric switching of spin to charge conversion, it's really essential that it can be done at room temperature. So it's kind of promising for applications. Then another important thing is that this property emerges from the bulk. So we believe that it can be like more robust in practice. And now we are trying to think about possible devices that can be designed based on these results. So, okay, this is, I had only 15 minutes and the topic was very complex. So I believe there are many questions. And yeah, I look forward for the discussion.
Great. Thank you very much for this very clear and interesting talk, Jagoda. So the talk is open for questions, so please use the chat and I'll relay this. So I have a question. So you mentioned, maybe this is just some basics that I don't quite grasp, but you mentioned some spin textures.
Mm-hmm.
What are these? What are you referring to exactly as spin textures in this particular material?
Well, that the bands reveal the spin polarization. So it's the, I mean, it's something that you can also detect. It's in maybe what can be, what is not so common is that we are talking about reciprocal space. So it's a spin texture of the reciprocal space.
Right,
I believe
right,
that
right.
this was the confusion. So it's not in a real space.
Right.
It's
So
non-magnetic material.
Right. So you're not talking about ordered magnetic states, but something.
No. It's yeah. This is actually quite relevant. It's non-magnetic material, so we may have quite interesting spintronic functionalities without using ferromagnets. I mean, in the experiment we used, but in principle, the goal is to eliminate ferromagnets from the most important component of the setup.
Okay, thank you. So questions? Any other questions? No. So how I mean, how do you have a feeling of how important, obviously in these kinds of when you start to combine these materials with other systems, so like at the end you mentioned spin pumping effects and so on, coupled into iron, I imagine that these interfaces, different material interfaces, will have a very important effect on the band structure of germanium telluride.
You mean other components of interface?
Yeah.
Actually, they do. We have previously we have performed a more detailed study on the interface between iron and germanium telluride. So it has lots of implications, but actually the surface of germanium telluride is in general quite interesting. And what is happening when we put iron on top is that we are losing, for example, these surface states. But what is very relevant here is that we are convinced that the Hall effect, the spin Hall effect, is driven by bulk states. And the bulk states are not affected much by the rest of the setup, by the interface. So actually it's affected, I mean, it's quite shallow. It's maybe 2 layers, and deeper we still have these bulk states. So, I mean, we are convinced that this is quite promising because it will be more robust. It will be, I mean, maybe we can change this interface and there will be no huge change.
Okay. So just maybe one last question. So from Unit, so Felix, he asks, so how conducting is a germanium telluride? Because it's usually hard to inject spins in a semiconductor.
Okay, how conducting it is? Okay, I think it's, I gave this value, actually I gave this value here. It's, yeah, I mean, I gave this value quite precisely. It's 5 to 10 to 3 per ohm per centimeter.
Okay, so, okay, maybe just one last question from Unit. So, question from Hamayun. As I understood, every p-type doping can roughly distort the polarization of germanium telluride, in opposite to n-type ones. Is this correct?
Well, germanium telluride is intrinsically p-type doped. I have shown this piece of plot because I think it's quite interesting direction to pursue. Yeah, we noticed that because the mechanism of ferroelectricity is based on lone pairs. So nothing can happen with lone pairs when we do put electrons. This would mean that we will not lose the polar distortion, and maybe it's also a promising way of probing these effects, because we will not lose ferroelectricity at all. But such samples, I don't know what is the stage of the experiment. You can do the N-type doping, but we don't have yet any relevant results. So, but I mean, I have shown it because I believe it's an interesting direction to check.
Okay. So thanks for that. So I think we will wrap it up here to get things moving. So thanks again for this very interesting talk, Yagami. So our next contributor talk is from Alberto Anodon, another contributor talk. So it will be on the spin orbit talk from the introduction of copper interlayers in platinum, copper, cobalt, platinum nanolayer structures for spintronic devices. Affiliated with India Nanociencia, but I see Barcelona, so I don't know, maybe it's just a localization for them. Anyway, the screen is yours.
Thank you. So yeah, I'm working now at India Nanoscience, and Barcelona is my second surname. So now I'm working in Madrid right now. So today, thank you for the introduction. Also, thank to the organizers for giving me the opportunity to present this work. I'm going to talk now about how, by introducing a copper interlayer in a platinum cobalt platinum symmetric trilayer, we can induce significant spin orbit torques. And I will try to convince you how this is interesting for the sake of spintronic devices. So basically, we all know here about magnetic RAM memories, and magnetic RAM memories are very interesting because they are non-volatile. So basically, when you remove the power, you still have what's written there. But also, they are almost infinite reading and writing. So these two things make them very interesting for memory applications. Basically, there have been two main approaches for making magnetic RAM memories, and the first one, and the classic approach, has been to use the spin transfer torque effect. And basically, here we have magnetic tunnel junctions, and we already know about them. And in here, you basically have a free layer, a tunneling barrier, and a reference layer, and you have spin polarized currents going through this system, which are able to write when they are high enough. So basically, you switch the magnetization of the magnetic layer. This approach is very interesting, but it has some drawbacks that we have to take into consideration. And the first one is that we need very high current densities to switch and to write basically the ones and zeros in the bit. And this sometimes may cause the tunneling barrier to be damaged, and this can destroy basically the bit of memory. Also, since the writing and reading goes to the same channel, there can be some false writing when you are trying to read. So to overcome both these issues, it has been proposed that a good way is to use the spin orbit torque. And I will go into more detail in the next slide, but basically here we have a three-terminal device instead of a two-terminal one. So reading and writing go through different channels, and we are already overcoming some of the issues that we had in the spin transfer torque memories. But this does not come without any kind of limitations. And to use a spin orbit torque to write and to read and to write efficiently, basically, we need to have an in-plane magnetic field, because otherwise you need a very high current to switch the magnetic layer. Luckily, there already are some groups that have come with some ways to overcome this issue. So this is very promising. The spin orbit torque and RAMs are very promising for future memory applications. The origin of all of these spin orbit torque memories comes, as we all know, from spin orbit coupling. And since we are in the spin orbit physics, you probably already know about where I am going to talk. So from spin orbit coupling, you can have many interesting phenomena, such as the Lositsky-Mori interaction, which was previously discussed in some of the talks. And this can give rise to chiral domain walls and chiral spin structures, such as schemions, which are very promising for memory applications too. But there is a handful of very interesting phenomena coming from here, like spin orbit coupling into the materials, Rajba interfaces, or topological surface states. But we are going to focus here in the spin charge current interconversion. which is basically the spin Hall effect. And if you go to the ordinary Hall effect, what you have here is a material in which you apply electric current in this direction. And then when you put a magnetic field like this, then you have a deflection of the electrons due to the Lorentz force. And what you have in the end here is a charge accumulation at the edges and basically an electric field in this direction. If you go to the spin Hall effect, what you have here is that when you apply an electric current into a system that has high spin orbit coupling, the scattering directions of up and down spins are different. So basically you have a spin accumulation at the edges of the sample, and this produces effective magnetic fields. And these effective magnetic fields can make modifications to the magnetization of a magnetic layer that you can put next to this layer with high spin orbit coupling. So this can produce, this can be as high as to produce the switching of this magnetic layer, and this is the way you write in the spin orbit torque memories. You can also do reading by some effects like the anomalous Hall effect, for example. Okay, so I've talked already about the spin Hall effect, and well, its inverse counterpart is basically when you have a spin current, it gets converted to a charge current or a charge accumulation. But it's also very interesting to notice that interfaces with a spin orbit coupling can also give rise to this spin to charge conversion. And basically, recently it has been predicted that when you apply a charge current in the in-plane direction of a spin orbit interfaces, there are ways that spin currents can be generated. Basically, we have selected the most relevant phenomena for this interfacial spin current. And the first one is the spin memory loss. And in spin memory loss is a decoherence effect. When you apply a spin current in the perpendicular direction to a spin orbit interfaces, the spin currents lose part of its coherence. You basically lose part of the polarization of this spin current. But also, as I said, when you apply an electric current in the in-plane direction, you can have phenomena such as spin filtering or spin precession. And spin filtering happens when currents with parallel and anti-parallel directions then have different scattering amplitudes when they transmit or reflect at the interface, and this gives rise to spin currents. In the case of spin precession, what we have is that when electrons experience an interfacial spin orbit field, they change its polarization, basically. And both these phenomena are able to generate spin currents from spin orbit fields at the interface. So in this study, they suggest that a very interesting system to study this interfacial spin current is the platinum, copper, and copper cobalt interfaces. So what we came up with is, as I said at the beginning, we introduce a copper interlayer in a platinum cobalt platinum symmetric system. Then we take the samples and we make whole bars patterning day by optical lithography. And we just by looking at the whole anomalous Hall resistance, we observed that the perpendicular magnetic anisotropy of the system decreased slowly when the copper thickness increases, but the samples are still perpendicularly magnetized up to 3 nanometers of copper. So basically, if we take these samples and measure the second harmonic signal of the voltage, what we see is basically that when we introduce the copper interlayer, we observe almost a 10-fold increase in the anti-damping torque and a slightly smaller one in the field like torque. If you see this problem without taking into account the interfacial effects, basically copper should be almost invisible to, almost transparent, sorry, to the spin currents, because copper has a very, very high spin diffusion length. So basically a spin current should go through copper as if there was nothing there. But what we are seeing is not that. Basically, the picture that we observe here is if you go to the symmetric system, then you have two contributions that compensate to each other, and then you don't have a net spin orbit torque. While in the case of the copper interlayer, you have one of the contributions which is larger than the other, and this gives rise to a net spin-orbit torque. So now, to understand how what's the origin of this difference in the spin-orbit torque, we are going to use the spin-Hall magnetoresistance effect. And luckily, we had Saul before me that gave a very nice introduction about what the spin-Hall magnetoresistance is. And basically, we have, as he said, we have two states of higher and lower resistance depending on the orientation of the spins in the upper and bottom layer. And this difference basically gives us information on how the system is now. So we made a spin-Hall magnetoresistance measurement with dependence of the thickness of the copper interlayer. What we observe here is that in the symmetric platinum cobalt platinum layer, we have a rather high spin-Hall magnetoresistance, but as soon as we introduce the copper interlayer, this is drastically reduced. Basically, this drastic reduction of the spin-Hall magnetoresistance is most likely going to be because of spin memory loss. And to understand this, what we did was we developed a drift diffusion model, and we can see here the up resistance and a small resistance when the field is perpendicular, is in the Y and Z direction. So what we did was we studied how the spin-Hall magnetoresistance depends first on the copper thickness. As I said before, copper is almost transparent. We see a small decrease of the spin-Hall magnetoresistance of the system when we change the copper thickness up to 20 nanometers. And this bulk drift diffusion does not explain the decrease of the spin-Hall magnetoresistance when we introduce the copper interlayer. So what we did is we introduced spin memory loss, and after introducing the spin memory loss in this copper cobalt interface, we observed that the spin-Hall magnetoresistance was drastically reduced, and the behavior that we are observing mimics very well what we observe experimentally for the sample with half a nanometer of copper. Then for larger thicknesses, we observe some dependence on the thickness of copper of the spin-Hall magnetoresistance, and this dependence is most likely due to the dependence of all these three spin current generation at the interface of those three phenomena that I explained before. But it's very challenging to separate all these contributions, since all of the phenomena have a very strong dependence on the thickness of copper. So basically, the message that you should take away from this talk is that we have observed an interfacial enabled increase of the spin-orbit torque by introducing a copper interlayer in between cobalt and platinum in a symmetric platinum cobalt platinum trilayer. This enhancement of the spin-orbit torque comes with a reduction of the spin-Hall magnetoresistance that gives us information on the origin of this increase of the spin-orbit torque, and we infer that the spin memory loss is the main responsible for this enhanced spin-orbit torque and this reduction of the spin-Hall magnetoresistance. So basically, all this what we can take from here is that we can use abundant materials such as copper for fabricating spintronic devices without the need to use some expensive and scarce materials such as platinum. And so with this, I'll be happy to answer you any questions you have.
Great. Thank you very much for this very interesting talk and helping us stay on time. So the talk is open to questions from the audience. Please use the chat window. So let me get things started. So when you make these kinds of measurements, are like artifacts such as Ørsted fields and things like that important to take into?
You mean the spin-orbit torque? Yeah. You basically have to consider all the artifacts, and there's already a lot of literature about it. So basically, we have reduced, subtracted the possible artifacts from planar Hall effect and so on when you do these measurements.
Okay. Okay, so a question from Felix. So do you know why you have the thickness dependence of the spin memory loss?
So what we think here is, as I said, this is a very challenging interpretation because you have many different things at the same time. You have the spin filter, and you have the spin precession, and you have the spin memory loss, and these three effects have a strong dependence on the copper thickness. They are not isolated to this dependence. So basically, you have three things going on at the same time, and separating all of them is challenging. So what I say is this is like the composition of several interfacial effects.
Okay. So on this drift diffusion model that you speak about, so this is mainly, so there's really a mix of what, there's a lot of CIP kind of transport. It's mainly a CIP dominated type of transport, right?
I'm not sure what you're saying, but basically this is a Valency model.
It's valley felt. Okay,
Yeah.
because I thought, I mean, if I recall correctly, that when we first started to do CIP GMR, it appeared that the transport models were actually a bit more involved than valley felt. So I was just wondering whether this was something that was been taken into account in this model.
As I said, this is basically Valency. Yeah.
Okay.
So you take the diffusion equations and you take the boundary conditions and then you can calculate all of this. Then you can introduce the spin memory loss by reducing the spin current through any interface you want, and you obtain by resolving the equations, you obtain this kind of profiles for the spin current and the spin accumulation.
Okay, so I have a question here from Saul. Can you distinguish between copper enhancing the spin orbit torques and the copper layer blocking the SOT contribution from the top copper platinum interface?
Yeah, this is basically what we try to do by analyzing the spin Hall magneto resistance. As I said, there are many things going on at the same time, but we think that basically by our interpretation from the diffusion model, we see that this decrease of the spin Hall magneto resistance mimics very well the result for our model. So we think that this decrease of the spin Hall magneto resistance most likely comes from a spin memory loss. But as I said, this is not the whole picture, because to have the whole picture, you need to put all the phenomena together, and it is very challenging to do in theory this.
Okay, great, thanks. Are there any other questions from the audience? So if not, let me thank you on behalf of everyone again, Alberto, for this very nice and clear talk.
Thank you.
Thanks. Okay, so the final talk for this session will be given by Lina Jonsson from Nguyen University of Science and Technology in Trondheim. And so her talk will be on the magnetization reorientation due to the superconducting transition in heavy metal heterostructures. So the screen is yours.
Thank you for the introduction. Let me just put on the pointer there. Okay, I'm going to talk about reorientation of the magnetization in superconductor ferromagnet structures. And we'll look at the system with a superconductor, conventional superconductor, and a homogeneous ferromagnet, where we have a normal heavy metal at the interface that boosts the Rajba spin-orbit coupling. Previously, it has been shown that by rotating the magnetization of the ferromagnet, you can change the critical temperature of the superconductor. We wanted to look at the reciprocal effects. That is it possible to reorient the magnetization by decreasing the temperature below the superconducting critical temperature? That is, can we use the superconducting phase transition to affect the magnetization direction of the ferromagnet? So why would we expect this? Well, in conventional superconductors, electrons form singlet Cooper pairs, and this singlet Cooper pair amplitude is proportional to the superconducting condensation energy in the superconducting gap. And therefore, a decrease in the singlet amplitude leads to a weakening of the superconducting condensate, and therefore also a decrease in the critical temperature and an increase in the free energy of the system. And since the minimum of the free energy is the ground state of the system, we can use the free energy to find which magnetization direction is preferred. So how do we manipulate the singlet amplitude? We do this by combining the superconductor with another material so that superconducting Cooper pairs can leak into the other material. And also, if this material introduces some kind of symmetry breaking, we can create equal spin and opposite spin triplet Cooper pairs from the singlets. So let's look at some systems where this happens. If we first look at a superconductor ferromagnet structure, where we just have one homogeneous ferromagnet, the spin splitting of the energy bands in the ferromagnets leads to a mixing of spin up and spin down, so that we get a mixing of the singlet and opposite spin triplet amplitudes. However, this system is invariant under rotation of the magnetization in the ferromagnet, and also both the singlet and the opposite spin triplet amplitudes does not survive for long distances inside the ferromagnet, since the spins try to align with the magnetization and they're opposite in the first place. If we instead include a second ferromagnetic layer which is misaligned with the second one, then the misalignment between the magnetizations rotates the opposite spin triplets into equal spin triplets. And since these are already aligned with the magnetization, they can survive for much longer distances inside the ferromagnet. Also, since the creation of these are dependent on how much the ferromagnets are misaligned, this effect depends on the direction of the second ferromagnet. So we can control the singlet amplitude by rotating one of the ferromagnets. In this way, we can control the critical temperature and the free energy. What we instead do in our system is that we have only one homogeneous ferromagnet, but we introduce Rajba spin-orbit coupling through the heavy metal layer. And in this way, we can create equal spin triplets, and the amplitude is dependent on the direction of the ferromagnet in a similar way as in the system where we had two ferromagnets, but we can manage with just one ferromagnet. So to approach this problem, we use the Bogoliubov-Duchenne framework. And the good thing about this is that we can combine any combination of atomically thin layers of materials. And also that since this is a ballistic limit framework, we can model the crystal structure of the lattice. So we considered a 3D cubic lattice and this Hamiltonian, where we have a hopping term and a chemical potential term that is present in all three of the layers, where we have tight binding nearest neighbor hopping. And we also have a superconducting term, a Rajba spin-orbit interaction term, and a ferromagnetic term that are non-zero in their respective materials. The superconducting on-site interaction is treated by a mean field approach, where we solve for the superconducting gap delta iteratively. The Rajba term has a strength lambda and a direction n perpendicular to the interface, and here sigma is the vector of polar matrices and d is a vector from latticite I to latticite j. The ferromagnetic term has an exchange interaction h, which is also shown in the model figure as a green arrow. So what we do is we numerically diagonalize this Hamiltonian to find the eigenenergies and eigenvectors, and we use these to calculate the free energy and the critical temperature. So let's start looking at some free energy plots. First, we considered a rotation of the magnetization from in-plane direction to out-of-plane direction compared to the interface. And for, as you see in panel A, the minimum of the free energy is for an in-plane magnetization direction. And in this panel, we have a temperature above the superconducting critical temperature. If we decrease the temperature below the critical temperature, as we have done in panel B, we see that the minimum of the free energy shifts to an out-of-plane magnetization direction. So what we see is that we have a reorientation of the magnetization from in-plane to out-of-plane. In panel C and D, we have plotted the exact same free energy curves for the same temperatures, but with a system where we instead have a normal metal and no superconducting phase transition. Then we see that there is no shift in the minimum of the free energy, so this reorientation must be caused by the superconducting phase transition. In this model, we have not yet taken into account the shape anisotropy of the ferromagnet, so for this to happen, we would expect that we need a thin ferromagnetic layer with as weak shape anisotropy as possible. We also considered an in-plane rotation of the magnetization, and what we found was that if we are above the critical temperature, as in panel A, and slightly below the critical temperature, as in panel B, we have a preferred magnetization direction along the cubic axis. If we further lower the temperature, so it's well below the critical temperature, a new minimum appears at the pi/4 direction compared to the cubic axis that is in the 110 direction. So we have a pi/4 rotation of the magnetization. Again, we see that if we don't have a superconducting phase transition, nothing happens. Since this effect is weaker than what we saw for in-plane to out-of-plane reorientation, we would expect that we need a stronger shape anisotropy so that the magnetization is enforced to be in plane in the first place. Next, I want to mention a work done together with our collaborators led by Farkad Aliyev. This is an experimental work mainly, where they found a change in the magnetic anisotropy of a vanadium magnesium oxide iron system due to the superconducting phase transition. As is sketched in this figure, for temperatures above the critical temperature, we have minima of the anisotropy in the directions of the cubic axis, so that the magnetization prefers to stay along the cubic axis. While below the critical temperature, new minimum occurs so that we can rotate the magnetization by pi/4, as we've shown in our theoretical predictions. This is caused by a strengthening of the condensate due to a weakening of the spin-orbit coupling assisted conversion for this direction. Also in this model, in addition to the superconductor heavy metal ferromagnet layer, we have a measuring hard layer of iron cobalt, and we have a slight, in addition to this change in the free energy we saw before, that it prefers anti-parallel alignment of the two magnetizations. So what they showed was that if the magnetization are anti-parallel in the first place, then you can have, for normal metal, if you apply an external field in this direction towards 2 pi, you can force the magnetization to go to this minimum at 3 pi/4 if you're in the normal state. But for lower temperature, when you're in the superconducting state, the magnetization will instead be trapped in this minimum at 5 pi/4. And this is exactly this pi/4 rotation that we saw in our theoretical prediction. If you're more interested in these experimental results, I encourage you to see the pre-recorded talk by Cesar González Ruano, who was the first author of this paper, and this is contributed to this mini colloquium. Last, I want to show you some results we have on the critical temperature. As I mentioned earlier, it has already been shown that the critical temperature changes when we rotate the magnetization of the ferromagnet. And the previous results are what you see in this panel A, where it has been shown both experimentally and in the diffusive limit that we have a suppression of the superconducting critical temperature for in-plane magnetization compared to out-of-plane magnetization. What have not been shown before, and what we were able to show in the ballistic limit, is that in addition, we have a modulation in the critical temperature for in-plane rotations of the magnetization, where the critical temperature is further suppressed when the magnetization is along the cubic axis compared to when it is middle between the cubic axis. So just to sum up our results, we have predicted an in-plane to out-of-plane magnetization reorientation for thin ferromagnetic layers. This has not yet been shown experimentally. We have also predicted a power in-plane rotation of the magnetization for layers of the ferromagnet that are thick enough to enforce in-plane magnetization. And this has been supported by experimental results. And we have found an additional in-plane critical temperature modulation in the ballistic limit compared to what has been found experimentally and the diffusive limit before. Thank you very much for your attention, and you're free to ask questions.
Okay. Thank you very much, Lena, for this very interesting talk. So the talk is open for questions from the audience. So please use the chat window. So I was just wondering, when you mentioned the theory, so you have this Bogoliubov-Lejeune Hamiltonian, and you're comparing the predictions of this to some experiments. Do you have a feeling of how important a realistic band structure would be? Is this something that's intrinsically, is this something that you would need to take into account in detail in general, or do you think just the general features get captured from what is essentially, I guess, in terms of the ferromagnetic part, I guess it's like an SD type model, right?
Yeah, the thing with this is that this model is very good at showing qualitatively what happens, but since we explicitly modeled the lattice structure of the system, we cannot take into account as many lattice points as there would actually be in an experimental sample. So everything must be scaled by, say, the thickness of the layers must be comparable to the superconducting condensation, no, the superconducting coherence length. We can make that kind of comparisons, but the actual physical, like the size of the different parameters and exact band structure will be a little bit different than what it will be in a real sample.
Okay. So, are there any other questions from the audience? No. Based on this theory, are there ways to kind of maybe not predict directly, but suggest certain material combinations that would be better than others to measure these effects?
You mean actual materials?
Right, right.
No, we can't really use this model to find which which materials are more appropriate. We only can say that, like for this in-plane to out-of-plane switch, we need the shape anisotropy to be as weak as possible. So we will need a ferromagnet that has a weak shape anisotropy, and also heavy metal that boosts the Rajba spin-orbit coupling. But other than that,
Okay.
yeah.
Okay. So, any other questions from the audience? I guess everyone's keen to get to lunch or something. Or if not, then let me thank you on behalf of everyone for this very interesting talk. Yeah. And thank you to all the speakers of this session. It's been an interesting, I think, experience for everyone, but I think it's gone quite well. So we have a lot of interesting sessions left in this symposium. So we look forward to seeing you all again in a later session. Okay, so let me close the session now. So thank you very much. Bye.